On November 23, 2022, the most expensive telescope ever built pointed at a tiny speck of light near Jupiter and collected data for a few minutes. That is all it took. A few minutes of observation from the James Webb Space Telescope, aimed at a moon most people could not pick out of a lineup, and two independent research teams working on opposite sides of the country pulled from that data the same conclusion: carbon dioxide on the surface of Europa, and it almost certainly came from the ocean underneath, not from meteorites, not from Jupiter's radiation tearing apart surface molecules, from the ocean, a liquid saltwater ocean hiding beneath somewhere around 29 kilometers of ice on a moon smaller than our own, orbiting a gas giant nearly 800 million kilometers from Earth. An ocean that by most estimates contains 2 to 3 times more water than every ocean, river, lake, and glacier on our planet combined. And now we know that ocean contains carbon. Think about what that means for a moment. When scientists talk about the ingredients for life as we understand it, they keep coming back to the same short list: liquid water, an energy source, carbon chemistry, nutrients. For decades, Europa had the water and the energy, and that was compelling enough to make it the most intriguing target in the solar system for astrobiology. But carbon was missing from the direct evidence. It was assumed, modeled, predicted, but not observed in a way that could be tied specifically to the ocean. The September 2023 publication of those JWST results filled that gap, and it did so with a level of spectral detail that no previous instrument could have achieved. But what does not make it into most headlines is the gap between ingredients and outcome. Having the ingredients is not the same as having the recipe. Detecting carbon on the surface of Europa does not mean something is alive in its ocean. It does not even mean the ocean is habitable in any meaningful sense, because between that carbon dioxide sitting on the surface and the liquid water 60 to 150 kilometers below, there is an ice shell so thick it would take you 3.5 Everests stacked on top of each other to get through it. And we have never seen through it. We have never sampled the ocean. We have never directly confirmed the ocean even exists, not with the certainty that word implies. Everything we know about Europa's ocean, we have inferred. Brilliantly, rigorously, with some of the cleverest experimental physics of the last 30 years. But inferred. So the question that matters is not whether Europa has the ingredients for life. After the JWST results, it almost certainly does. The question is whether those ingredients are actually in the same place, at the same time, in the right combinations, doing the right chemistry. Whether the ocean is not just wet, but genuinely habitable. And that question is nowhere near answered. Every time a new discovery appears to close the case, something else opens it back up. That pattern, that maddening cycle of almost knowing, is the real story of Europa. And it is the story that Europa Clipper, the most ambitious ocean world's mission ever launched, is traveling 5 years across the solar system to resolve. Let us start with what the telescope actually saw. The JWST data came from Guaranteed Time Observation Program 1250, led by Geronimo Villanueva at NASA's Goddard Space Flight Center. The observations used the telescope's NIR spec instrument in a configuration called Integral Field Unit mode, with high-resolution gratings designated G235H and G395H, giving a spectral resolution of roughly 2700. In practical terms, that means The telescope was slicing near-infrared light into extremely fine wavelength bins, covering everything from about 1.7 to 5.2 micrometers. It observed Europa's leading hemisphere, the side facing forward, in its orbit around Jupiter, centered on a sub-observer longitude of roughly 93 degrees west. Two teams analyzed the same dataset independently. Samantha Trumbo and Michael Brown at Caltech published "The distribution of CO2 on Europa indicates an internal source of carbon" in Science on September 21st, 2023. The same day, in the same journal, Villanueva and colleagues published "Endogenous CO2 ice mixture on the surface of Europa and no detection of plume activity." Two papers, back-to-back, from teams that did not coordinate their analyses, reaching the same conclusion. That kind of independent replication from the same raw data is about as strong as observational science gets. Both teams detected 4 spectral features of carbon dioxide ice on Europa's surface. The most critical was the asymmetric stretch band between 4.25 and 4.27 micrometers. Previous instruments had seen this feature as a single absorption dip. JWST resolved it into something no one had seen before, a double-peaked minimum. That level of spectral detail was simply impossible with earlier telescopes. It revealed not just that CO2 was present, but specific information about how the CO2 was mixed with other materials on the surface. Villanueva's team also resolved a 2.7 micrometer combination band of crystalline carbon dioxide for the first time and identified the CO2 as existing in a mixture with water ice and methanol at a temperature of about 114 Kelvin. And then Villanueva's group did something particularly clever. They detected a faint spectral feature at 4.38 micrometers, corresponding to carbon-13 CO2, the isotopically heavier version of carbon dioxide. From this, they measured the carbon-12 to carbon-13 ratio at 83 plus or minus 19, which is consistent with typical solar system sources. That ratio alone cannot tell you whether the carbon has a biological origin or not. The uncertainty is too large, but it does confirm that carbon is not exotic. It belongs in our solar system's chemistry. Now here is where the geography becomes the argument. Carbon dioxide on Europa's surface is not evenly distributed. It is overwhelmingly concentrated in a region called Terra Regio, a stretch of chaos terrain about 1,780 kilometers across, centered at roughly 10 degrees south latitude and 75 degrees west longitude. There are weaker concentrations in another chaos region called Pauis Regio, but Terra Regio is where the signal screams. 4 lines of evidence converge to say this CO2 came from inside the moon, not from external sources. First, the geographic correlation. CO2 maps onto chaos terrain, the specific type of geological feature where subsurface material is thought to reach the surface. If the carbon dioxide were delivered by meteorites, you would expect it scattered randomly or concentrated in impact craters. It is concentrated in exactly the places where the interior vents upward. Second, Terra Regio is already known to contain ocean-derived material. In 2019, 3 years before the JWST observation, Samantha Trumbo had used the Hubble Space Telescope to detect sodium chloride, table salt, concentrated in the same region. That salt almost certainly came from the ocean. The CO2 sits on top of it, in the same terrain, in the same geography. 2 independent, endogenous signatures co-located in the same place. Third, carbon dioxide ice is thermodynamically unstable at Europa's surface conditions. The surface temperature averages around 110 Kelvin, -163 Celsius, which sounds cold enough to preserve anything. But Europa's surface is also bombarded by intense radiation from Jupiter's magnetosphere. Pure CO2 ice gets destroyed by that radiation on relatively short geological timescales. Its presence means it has been recently supplied, not millions of years ago. Recently, something is actively delivering carbon dioxide to the surface of Terra Regio. Fourth, and this is the argument that closes the door on the remaining alternative, Trumbo and Brown found no complex organic molecules on Europa's surface. This matters because there is one other way to produce CO2 at a planetary surface without an internal source. Radiation can break down complex organic molecules delivered by meteorites or cometary material, producing CO2 as a byproduct. If Europa's surface were littered with externally delivered organics, the CO2 could be a radiation product of those organics rather than something from the ocean. But the organics are not there. Without the raw material, that pathway does not work. Samantha Trumbo put it plainly in NASA's press release that accompanied the papers. We now think that we have observational evidence that the carbon we see on Europa's surface came from the ocean. That is not a trivial thing. Villanueva added context that hints at why astrobiologists find this result so electric. On Earth, life likes chemical diversity. The more diversity, the better. We are carbon-based life. But there is an important caveat embedded in Villanueva's other result, one that gets much less attention than the carbon detection. His team also conducted a sensitive search for water vapor plumes erupting from Europa's surface. They looked for fluorescence emissions from water, methane, ethane, methanol, and carbon monoxide. They found nothing. No plume activity detected, with strict upper limits on how much material could be escaping. This matters enormously, and we will come back to why. For now, just hold this in the back of your mind. The best telescope humanity has ever built looked at Europa for evidence of active water plumes and came up empty. So the carbon is there. It came from the ocean, but it is sitting on the surface, and the ocean is hidden beneath kilometers of ice. The obvious question is, how did it get from one to the other? What mechanism moves ocean material through 30 kilometers of frozen crust and deposits it on the surface in a specific geographically concentrated pattern? The answer, or at least the best candidate for one, lies in the most visually bizarre landscape in the outer solar system. Chaos terrain covers somewhere between 20 and 40% of Europa's surface, and it looks exactly like it sounds. Imagine a frozen lake the size of a continent, and then imagine something underneath that lake shattered it, not uniformly, not neatly, but violently, breaking the surface into polygonal blocks of ice, some of them kilometers across, that shifted, rotated, tilted, and then refroze in place. That is chaos terrain. It is as if someone took a jigsaw puzzle, shook the box, and then glued the pieces down wherever they landed. The archetype is Connemara chaos, a region imaged by the Galileo spacecraft at resolutions down to 9 meters per pixel. It sits at about 9.7 degrees north latitude, 87.3 degrees east longitude, and a careful analysis by Spawn and colleagues in 1998 identified 139 distinct polygonal ice blocks, what planetary scientists call ice rafts, floating in a matrix of refrozen material. 78% of those rafts had undergone horizontal translations, typically between 1 and 5 kilometers from their original positions. 81% showed rotation, with an average rotation of about 11 degrees. The cliff heights at the edges of these rafts reach roughly 100 meters. These are not small features. They are fragments of a continental ice sheet that was broken apart and then froze back together. The puzzle piece nature of Connemara chaos is so precise that researchers can literally slide the rafts back together, like reassembling a broken plate, to reconstruct what the surface looked like before the disruption event. Emily Martin of the National Air and Space Museum described it vividly. The surface got warm enough to break up into these little ice rafts. The entirety of Terra Regio is these broken up puzzle pieces floating around in this now solidified icy, slushy matrix. 3 theories compete to explain how chaos terrain forms, and the differences between them matter because they imply very different things about how connected the surface is to the ocean. The first is the melt-through model, proposed by Greenberg and colleagues in 1990. This is the most dramatic scenario. Ocean water melts completely through the ice shell from below, breaking the surface into blocks that literally float on exposed liquid water, or slush, before the whole thing refreezes. If this model is correct, chaos terrain represents windows that once opened directly onto Europa's ocean. Material exchange would be total. Ocean chemistry would reach the surface with minimal modification. But this model requires the ice shell to be thin enough for ocean heat to penetrate all the way through. And recent measurements suggest the shell may be too thick for that. The second is the diapiric upwelling model, proposed by Head and Pappalardo in 1990. Picture a lava lamp, but with ice. Warm, buoyant ice near the base of the shell rises slowly through the colder, denser ice above it, like a thermal plume. When these warm ice diapirs reach the surface, they disrupt and fracture the overlying crust. This model is supported by the observation that Connemara chaos sits about 250 meters higher than the surrounding terrain, consistent with warm material pushing up from below. It does not require the ocean to breach the surface, but it does allow ocean-derived chemistry to be carried upward by the warm ice. The third model is perhaps the most intriguing. In 2011, Brittany Schmidt and colleagues published a study in Nature proposing vast lens-shaped lakes trapped within the ice shell itself, potentially larger than North America's Great Lakes. These subsurface lakes would form when tidal heating melts pockets of ice within the shell, and when they grow large enough, the overlying ice collapses into them, producing chaos terrain at the surface. In this scenario, the chemical pipeline from ocean to surface has an intermediate step. Ocean water feeds subsurface lakes. Lakes destabilize the surface, and lake chemistry reaches the open surface when the collapse occurs. All 3 models agree on one thing. Chaos terrain is where Europa's interior communicates with its surface. They disagree on the directness and completeness of that communication. And that disagreement matters because the habitability question depends not just on what is in the ocean, but on whether material cycles between the ocean and the surface in both directions. Can surface oxidants, the molecules created by Jupiter's radiation bombardment, make it down to the ocean? Can ocean nutrients make it up to the surface? The answer determines whether Europa's ocean is a sealed, isolated chamber or an actively cycling chemical system. In 2025, the cycling question got a dramatic new piece of evidence. Richard Cartwright at the Johns Hopkins Applied Physics Laboratory and his colleagues published a study in the Planetary Science journal analyzing the same JWST NIS-spec data from November 2022, but this time looking at wavelengths between 1.48 and 5.35 micrometers, with a focus on the water ice itself. What they found surprised everyone. For decades, scientists had assumed Europa's surface was coated in a thin layer of amorphous water ice, roughly 0.5 millimeter deep. Amorphous ice is water ice whose crystalline structure has been destroyed by radiation. Jupiter's magnetosphere bombards Europa's surface with charged particles at energies comparable to a particle accelerator, and this bombardment systematically destroys the orderly crystal lattice of water ice, turning it into a disordered, glassy form. The crystalline ice that should naturally exist at Europa's surface temperature was assumed to survive only at depth, protected beneath this amorphous radiation-damaged veneer. Cartwright's team found crystalline water ice sitting right there on the surface. In Tara Regio and Powys Regio, identified by a diagnostic Fresnel peak at 3.1 micrometers, crystalline ice that should not exist at the surface was plainly present. The implication hit immediately. Thermal recrystallization, the process by which amorphous ice reorganizes back into crystalline form when warmed, is outpacing radiation-driven amorphization. And it is doing so on a time scale of fewer than 15 days. 15 days, not 15,000 years, not 15 million years. 15 days. That is how fast the surface of Tara Regio is being refreshed. Co-author Ujjwal Raut of the Southwest Research Institute spelled it out. Our data showed strong indications that what we are seeing must be sourced from the interior, perhaps from a subsurface ocean nearly 20 miles beneath Europa's thick, icy shell. The chaos terrains showed lower bond albedos between 0.4 and 0.6 compared to the brighter northern regions at 0.7 to 0.8, consistent with warmer surface temperatures driving faster recrystallization. And the isotopically heavy carbon-13 CO2 feature at 4.38 micrometers appeared almost exclusively at southern latitudes within these chaos regions. Cartwright concluded, where is this carbon-13 CO2 coming from? Every road leads back to an internal origin. But here is where the maddening cycle begins again. The crystalline ice discovery tells us that material is being refreshed at the surface on timescales of days. It tells us the pipeline from interior to surface is active, vigorous, geologically recent, but it does not tell us whether the pipeline works in both directions. And that bidirectional flow is what the habitability case really needs, because the ocean's energy budget may depend critically on surface oxidants making the return trip downward through the ice. We will get to that problem. But first, we need to talk about the ocean itself, because for all the excitement about what JWST has found on Europa's surface, the single most important thing to understand about Europa's ocean is that no one has ever seen it. Everything we know about this ocean, every claim about its depth, its volume, its salinity, its temperature, derives from measurements made indirectly. The ocean is inferred, not observed, and the strength of that inference varies enormously depending on which property you are asking about. The existence of the ocean itself rests primarily on one measurement, and it belongs to a woman who was 97 years old when Europa Clipper launched and is still working on the mission. Margaret Kivelson was born on October 21, 1928. She attended Harvard in the first class after World War II, where courses were no longer gender segregated. She earned her doctorate under Julian Schwinger, the Nobel laureate in physics, and she was his only female doctoral student out of more than 70. She gave birth to her first child while still in graduate school, at a time when the prevailing expectation was that a woman who became a mother would leave science permanently. She did not leave, but recognition was slow. It was not until 1973, when she received a Guggenheim Fellowship, that she felt, in her words, for the first time the sense that I was being taken seriously as a scientist. She was 45 years old. By the mid-1990s, Kivelson was the principal investigator for the magnetometer instrument on NASA's Galileo spacecraft, which had been orbiting Jupiter since December 1995. Her instrument measured magnetic fields with exquisite precision, and she recognized something about Europa's orbit that offered a way to detect a subsurface ocean without ever touching the surface. Europa orbits within Jupiter's enormous magnetic field, which is tilted about 10 degrees relative to Jupiter's rotation axis. As Jupiter spins, the magnetic field wobbles, and Europa passes through slightly different magnetic environments during each orbit. If Europa contained a global layer of electrically conductive material, say a salty ocean, this time-varying external magnetic field would induce electric currents in that layer, and those currents would generate their own secondary magnetic field, a field that Kivelson's magnetometer could detect. In 1998, Korana, Kivelson, and colleagues published the first evidence of magnetic perturbations near Europa, consistent with such induction, in the journal Nature. But the initial data could not definitively distinguish between an induced field, which would change over time as the external field changed, and a permanent magnetic field, which would remain fixed regardless of Jupiter's orientation. A permanent field could arise from a metallic core, which would be interesting, but would tell you nothing about an ocean. The definitive measurement came from the E26 flyby on January 3, 2000. Kivelson designed the observation to exploit a moment when Europa was located far south of Jupiter's magnetic equator, a geometry that would produce a dramatically different induced field signature compared to previous flybys. If the field was induced, it would point in a direction determined by Jupiter's current magnetic orientation at the time of the flyby. If it was permanent, it would point in the same direction it always pointed. Regardless, the field varied. It pointed exactly where induction theory predicted it should point, given Jupiter's magnetic geometry at that specific moment. This was not a permanent dipole. It was an induced field generated by electric currents flowing in a global conductive layer beneath Europa's surface. The most natural conductor, a salty, liquid water ocean. Kivelson and colleagues published their result in Science in 2000, and it remains one of the most important discoveries in planetary science history. It did not prove the ocean existed in the way that, say, dropping a submarine into it would prove, but within the framework of electromagnetic theory, which is among the best tested frameworks in all of physics, the data required a conductive global layer, and the most physically plausible conductive layer by a wide margin was saltwater. 25 years later, Kivelson is the magnetometer team leader for Europa Clipper, the instrument that will make the definitive ocean measurement with 49 close flybys instead of a handful, is her intellectual descendant. But the magnetometer data, powerful as it is, tells you less than you might think about what the ocean is actually like. It constrains the electrical conductivity of the conductive layer, requiring it to exceed roughly 0.06 Siemens per meter, which is consistent with salty water, but it cannot precisely determine the ocean's depth, its salinity, or its temperature. Those properties are entangled in the induction signal. A thin, very salty ocean produces a similar magnetic response to a thick, moderately salty one. For depth, the best current estimate comes not from Galileo, but from a spacecraft that was never designed to study Europa at all. NASA's Juno spacecraft, in orbit around Jupiter to study the planet itself, flew past Europa on September 29, 2022, passing just 360 kilometers above the surface. Its microwave radiometer, designed to peer into Jupiter's atmosphere, was turned toward Europa instead. The data, published in Nature Astronomy in January 2025 by Levin and colleagues, yielded an ice shell thickness of 29 plus or minus 10 kilometers for pure water ice, reduced by about 5 kilometers if the ice contains dissolved salts. This was a major result. For nearly 20 years, the Great Thickness Debate, as Billings and Kattenhorn named it in a 2005 review paper, had divided Europa researchers into thick shell and thin shell camps. Estimates ranged from a few kilometers to over 30. The thin shell camp pointed to the chaos terrain as evidence of easy communication between ocean and surface, implying the ice could not be very thick. The thick shell camp pointed to the large-scale topography, crater relaxation, and thermal models suggesting the ice needed to be much deeper. Juno's measurement, the first capable of actually discriminating between the two models, landed firmly on the thick side. 29 kilometers, give or take 10. Below that ice lies the ocean itself. NASA's official estimate puts it at 60 to 150 kilometers deep, giving Europa a total water and ice layer of roughly 100 kilometers. The ocean's volume works out to approximately 3 billion cubic kilometers. Earth's oceans contain about 1.335 billion cubic kilometers. So Europa's ocean holds somewhere between 2 and 3 times more liquid water than exists on our entire planet. NASA tends to use the conservative about twice figure, which holds across most reasonable depth assumptions, but the actual ratio could be higher. The numbers are worth pausing over. Europa's diameter is only about 3,121 kilometers, roughly 90% the size of our moon. Its surface area is approximately 30.6 million square kilometers, almost exactly the area of Africa. And packed beneath that modest surface is an ocean that dwarfs anything on Earth. At 60 to 150 kilometers deep, it is 6 to 14 times deeper than the Mariana Trench. The pressure at the ocean floor reaches roughly 1,300 to 2,000 atmospheres at the greatest depths, which is extreme, but actually lower than what you would get at equivalent depths on Earth. Because Europa's surface gravity is only about 13% of ours, the ocean temperature sits near the freezing point of water, approximately 0 degrees Celsius, possibly a bit below if the water is very salty. That sounds cold, but it is warm relative to the surface, which averages around negative 163 Celsius. The temperature contrast from frozen wasteland at the surface to liquid water below is maintained by tidal heating. Jupiter's gravity flexes Europa as it orbits in its slightly elliptical path, an ellipticity maintained by the gravitational tug-of-war between Europa, Io, and Ganymede in their 1 to 2 to 4 Laplace orbital resonance. This tidal flexing generates roughly 1 terawatt of heat globally, enough to keep the ocean liquid despite Europa being more than 5 times farther from the Sun than Earth. And here is a detail that matters more than any other for the habitability question. The ocean sits in direct contact with Europa's silicate, rocky mantle, not floating above a layer of high-pressure ice, as is the case for the deeper oceans hypothesized inside Ganymede or Titan. Rock and water touching. On Earth, every known hydrothermal vent ecosystem, every black smoker on the mid-ocean ridge, every alkaline seep in the Lost City field derives its energy and nutrients from the interaction between hot rock and seawater. If something similar occurs on Europa's seafloor, the ocean would have access to chemical energy and dissolved minerals independent of anything happening on the surface. But, and this is where the latest research introduces a genuinely uncomfortable uncertainty. A study published in January 2026 by Byrne and colleagues in Nature Communications cautioned that Europa's seafloor may be geologically quieter than previously assumed. The models that predicted vigorous hydrothermal activity were built on assumptions about tidal dissipation in Europa's rocky interior, and those assumptions may be too optimistic. If the seafloor is relatively inert, if hydrothermal vents are rare or absent, then the ocean's chemical energy budget looks very different. It becomes much more dependent on what happens at the surface, on whether radiation-driven oxidants can somehow make it through 30 kilometers of ice to reach the water below. So here is where we stand. The ocean almost certainly exists. It is enormous. It contains carbon. It contacts rock. It has been liquid for something like 4.5 billion years, roughly the same span over which life arose and evolved on Earth. But its chemistry is poorly constrained. Its salinity is uncertain across 5 orders of magnitude. Its energy sources may be more limited than assumed, and the mechanism that connects surface chemistry to ocean chemistry, the pathway through the ice that would allow radiation products to reach the water, remains more theoretical than observed. The JWST carbon detection did not close the habitability case. It sharpened it. It told us the ocean has carbon, but it also forced us to ask harder questions about how that carbon and everything else the ocean needs actually gets where it needs to go. To understand why those questions became even more pointed, we need to talk about salt. Specifically, we need to talk about a physicist at the Jet Propulsion Laboratory who built a miniature Europa inside a vacuum chamber, bombarded table salt with radiation, and accidentally solved a mystery that had confused planetary scientists for 20 years. Kevin Hand is the kind of scientist who does not stay behind a desk. He directs the Ocean Worlds Lab at JPL and is the author of Alien Oceans, a book Princeton University Press published in 2020 that NPR named one of the best books of the year. His research expeditions have taken him from the glaciers of Kilimanjaro to the dry valleys of Antarctica to submersible dives alongside James Cameron. But the experiment that changed Europa's science happened in a lab in Pasadena when NASA's Galileo spacecraft imaged Europa in the late 1990s. Scientists noticed that certain regions of the surface, particularly chaos terrain like Terra Regio, had a distinctly yellowish-brown discoloration compared to the bright white ice plains elsewhere. The natural question was, what is the yellow stuff? Galileo carried a near-infrared mapping spectrometer called NIMS, and NIMS detected spectral signatures consistent with hydrated salts on the surface. For years, the consensus interpretation was that these salts were primarily magnesium sulfate, essentially Epsom salt, which is common in carbonaceous chondrite meteorites and certain terrestrial evaporite deposits. This mattered because the composition of surface salts was thought to reflect the composition of the ocean. If the ocean were rich in magnesium sulfate, it would suggest an ocean dominated by sulfate chemistry, quite different from Earth's sodium chloride seas. The two types of oceans imply different formation histories, different water-rock interactions, different implications for habitability. The problem is that Galileo's NIMS operated in the near-infrared, and sodium chloride is essentially invisible in the near-infrared. Chloride salts do not have the distinctive absorption bands in that wavelength range that sulfate salts do. NIMS literally could not see sodium chloride, even if Europa's surface were covered in it. The apparent dominance of magnesium sulfate could have been an observational bias, not a chemical reality. This is where Kevin Hand's experiment comes in. In 2015, Hand and his colleague Robert Carlson at JPL created what they called Europa in a can. It was an ultra-high vacuum chamber, cooled to about 100 Kelvin, the temperature of Europa's surface, and they placed samples of sodium chloride inside it. Then they bombarded the salt with 10 kilo-electron-volt electrons, simulating the radiation environment Europa experiences from Jupiter's magnetosphere. Something remarkable happened. The initially white salt turned yellowish-brown. After about 20 hours of irradiation, which corresponds to roughly 10 to 100 years of exposure on Europa's actual surface, the NaCl had changed color to match the yellowish discoloration of Terra Regio as seen by Galileo. The match was not approximate, it was precise. The physics behind it involves what are called F-centers, a term borrowed from the German word Farbzentrum, meaning color center. When high-energy radiation hits a sodium chloride crystal, it can knock chlorine atoms out of their lattice positions, leaving behind vacancies. Electrons become trapped in these vacancies, and the trapped electrons absorb light at specific wavelengths, around 460 nanometers, which is in the blue part of the visible spectrum. Material that absorbs blue light appears yellowish-brown. The F-centers are, in a sense, visible scars left by radiation damage. Hand described sodium chloride as invisible ink on Europa's surface. Before irradiation, you cannot tell it is there. Galileo's infrared spectrometer could not detect it because uniradiated NaCl has no diagnostic infrared features. But once radiation creates F-centers, the salt reveals itself in visible light through its distinctive color. The laboratory result was suggestive, but not definitive. To confirm that Europa's yellow terrain was actually irradiated sodium chloride, someone needed to detect NaCl spectroscopically on Europa's surface. That detection came 4 years later from a scientist who had built her entire career around this moon. Samantha Trumbo is now an assistant professor at UC San Diego, but in 2019, she was a graduate student at Caltech, writing her dissertation on Europa under the supervision of Michael Brown. Trumbo combined backgrounds in astronomy, biology, and oceanography. an unusual mixture that positioned her precisely at the intersection needed for this work. Using Hubble Space Telescope data collected between May and August of 2017 in the visible light range, Trumbo, Brown, and Hand identified an absorption feature at 450 nanometers, matching the spectral signature of irradiated sodium chloride. The detection was published in Science Advances on June 12, 2019. Critically, the NACAC was concentrated in chaos terrain on the leading hemisphere, exactly the regions where endogenous material would be expected and where contamination from sulfur implanted by Jupiter's magnetosphere would be least severe. The trailing hemisphere of Europa gets hammered by sulfur ions sputtered from Io, Jupiter's volcanic innermost Galilean moon. Any surface chemistry study on the trailing hemisphere is contaminated by this external sulfur. The leading hemisphere is cleaner, and that is where the sodium chloride appeared. This result overturned nearly 2 decades of assumption. Europa's surface salts were not primarily magnesium sulfate. Sodium chloride was there, possibly dominant, and it had been hiding in plain sight because every previous instrument that looked for salts operated in wavelengths where NaCl is invisible. The Epsom salt ocean was, at the very least, incomplete, maybe wrong entirely, and the implications rippled far beyond surface chemistry. On Earth, the dominance of sodium chloride in seawater is a direct consequence of hydrothermal activity at mid-ocean ridges. When seawater circulates through hot basaltic rock, magnesium is captured by the rock through mineral reactions, while sodium is leached out and carried into the ocean. A sodium chloride ocean implies water-rock interaction at elevated temperatures. It implies hydrothermal circulation. It implies the kind of active seafloor chemistry that on Earth supports entire ecosystems independent of sunlight, or at least it implied that in 2019. In 2026, as we discussed, the Bern study raised the possibility that Europa's seafloor might not be as active as assumed. The sodium chloride signature is real, but whether it indicates currently active hydrothermal systems or relic chemistry from an earlier, more active geological period is now an open question. This is the pattern. Every major Europa discovery tells us something electrifying and then immediately introduces a new complication. Carbon from the ocean reaches the surface, but the ice is 29 kilometers thick. The pipeline from interior to surface operates on timescales of days, but we do not know if it works in reverse. The ocean contacts rock, but the rock might not be doing much. The salts suggest hydrothermal activity, but that activity might have slowed or stopped. And the next piece of the puzzle introduces perhaps the most paradoxical element of all. Jupiter's radiation, the same bombardment that makes Europa's surface one of the most hostile environments in the solar system, might also be the key to making the ocean habitable. Jupiter's magnetosphere is the largest structure in the solar system. If you could see it in visible light, it extends millions of kilometers in every direction, and its magnetic field is roughly 20,000 times stronger than Earth's. Europa orbits deep inside this magnetosphere, and it pays a ferocious price. Charged particles, mostly electrons and protons, accelerated to enormous energies, slam into Europa's surface continuously. The radiation dose at the surface is lethal to any known Earth organism within minutes. If you stood on Europa's surface in a spacesuit, the radiation would kill you long before the cold or the vacuum did. But this radiation drives chemistry. Specifically, it drives the production of hydrogen peroxide and molecular oxygen from water ice. When a high-energy particle strikes a water ice molecule on Europa's surface, it can break the molecule apart, producing hydrogen atoms and hydroxyl radicals. These fragments recombine in various ways, and one of the most important products is hydrogen peroxide, H2O2. Hydrogen peroxide was first detected on Europa by the Galileo near-infrared mapping spectrometer during observations on November 6, 1997, at a concentration of about 0.13% by number relative to water ice on the leading hemisphere. In 2013, Kevin Hand and colleagues mapped peroxide globally using the Keck Observatory in Hawaii and found concentrations of about 0.12% on the leading hemisphere, dropping to near zero on the trailing hemisphere, where sulfur contamination from Io apparently suppresses peroxide production or stability. Why does this matter for habitability? Because if that peroxide-bearing surface ice can somehow cycle into the ocean, the hydrogen peroxide decomposes into water and molecular oxygen, free oxygen. In a dark ocean with no photosynthesis, radiation-produced oxidants delivered from the surface could serve as the chemical energy source that life needs. It would be an elegantly indirect pathway. Sunlight and Jupiter's magnetic field create energetic particles. Those particles create oxidants on Europa's surface. Geological processes carry the oxidants through the ice into the ocean. And down in the dark, organisms use those oxidants the way aerobic life on Earth uses the oxygen produced by plants. Estimates of how much oxidant could reach Europa's ocean vary enormously, from 100 million to 1 billion moles per year. And those estimates depend heavily on assumptions about how efficiently material cycles through the ice shell. But even the low end is potentially interesting from a biological perspective. Some models suggest it could support a microbial biosphere, roughly comparable to the total biomass of Earth's deep ocean hydrothermal vent ecosystems. A 2024 study by Wu, Trumbo, Brown, and DeClear added an unexpected wrinkle. Published in the Planetary Science Journal, their paper revealed a strong spatial correlation between hydrogen peroxide and carbon dioxide in leading hemisphere chaos regions. That alone was interesting. But the truly striking finding came from laboratory experiments showing that trace amounts of CO2 mixed into water ice act as an electron scavenger, enhancing hydrogen peroxide production by 2 to 3-fold. Think about what that means. The carbon dioxide that JWST detected coming from the ocean does not just sit passively on the surface. It actively changes the radiation chemistry happening around it. It makes the surface produce more oxidant. If you imagine a cycle where ocean-derived CO2 reaches the surface, enhances peroxide production, and that enhanced peroxide eventually returns to the ocean, you have a feedback loop. The ocean seeds the surface with carbon. The surface responds by generating more of the oxidant the ocean needs. But that word, if, is doing an enormous amount of work, because the return trip from surface back down through 29 kilometers of ice to the ocean is the weakest link in the entire habitability argument. The surface to ocean pipeline is the critical unknown. Chaos terrain clearly moves material upward, but downward transport is harder to demonstrate. Tidal flexing of the ice shell could create fractures and zones of enhanced permeability, but modeling this process quantitatively is extraordinarily difficult because we do not have direct measurements of the ice shell's mechanical properties, its temperature profile, or its internal structure. And there is another problem. Jupiter's radiation does not just create useful oxidants, it also destroys organic molecules. Any biosignature, any complex molecular evidence of biological processes that reached Europa's surface would be shredded by radiation within a relatively thin surface layer, perhaps the top few millimeters to centimeters. This creates a frustrating paradox. The radiation that might make the ocean habitable by creating oxidants is the same radiation that would erase the evidence of habitability from the surface. If there were organisms in the ocean producing organic molecules, and those molecules rode the chaos terrain pipeline up to the surface, the radiation would break them down before any passing spacecraft could detect them. This is why the plume question matters so much, and it is why the JWST non-detection is so significant. A plume, a geyser of ocean water erupting through cracks in the ice, would shoot material from the ocean directly into space, bypassing the radiation-processed surface entirely. A spacecraft flying through such a plume could sample ocean water that had never been exposed to surface radiation, water that might still carry intact organic molecules, intact chemical signatures, maybe even intact microbial cells. On another moon, in another part of the solar system, this exact scenario has already happened. Cassini flew through the plumes of Enceladus repeatedly, tasting samples of an alien ocean, and what it found there redefined the search for life beyond Earth. But Europa is not Enceladus. And that comparison, the reasons Europa's case is both stronger and weaker than its smaller rival, is where the story goes next. But before we get to Enceladus, there is a story that needs telling about the plumes themselves, because the history of Europa plume detections reads less like a triumphant series of discoveries and more like a ghost story. Something appears. You look again. It is gone. You look a third time. Maybe it is there. Maybe it is not. The first detection came from Lorenz Roth and colleagues in December 2012, using the Hubble Space Telescope to observe Europa in ultraviolet light. They detected faint emissions from hydrogen and oxygen atoms consistent with water vapor being ejected from Europa's south polar region to altitudes of roughly 200 kilometers. The result was published in Science on December 12, 2013, and it electrified the planetary science community. If Europa had active water plumes, like Enceladus, then sampling the ocean might not require drilling through the ice at all. You could simply fly through the spray. But then Roth's team went back and looked again. They observed Europa at the same orbital phase in January and February of 2014. The same geometry, the same instrument, the same technique. Nothing. No plumes detected. They published the null result in the Proceedings of the National Academy of Sciences, and the implication was clear. Whatever had produced the 2012 signal, if it was real, was episodic. It came and went. It was not a permanent feature, like the geysers of Enceladus, which Cassini observed erupting continuously for over a decade. In 2016, William Sparks and colleagues at the Space Telescope Science Institute tried a completely different technique. Instead of looking for ultraviolet emissions from the plumes themselves, they watched Europa pass in front of Jupiter and looked for ultraviolet absorption. If water vapor were present above Europa's limb, it would block some of Jupiter's ultraviolet light, appearing as a dark silhouette. In 10 transit observations, They found plume-like features in 3 of them. 3 out of 10, estimated heights around 200 kilometers, similar to Roth's measurement. But again, the features were transient, appearing in some observations and absent in others. Then came perhaps the most tantalizing evidence of all, found not in new data, but in old data that nobody had thought to reanalyze. In 2018, Sanjay Jha at the University of Michigan and Margaret Keivelson revisited the magnetic and plasma measurements from Galileo's E12 flyby of Europa on December 16, 1997. During a roughly 3-minute stretch of that flyby, Galileo had passed through a region where both the magnetic field and plasma density showed anomalies consistent with the spacecraft flying through a localized plume of water vapor and ionized particles. The paper was published in Nature Astronomy, and it suggested that Galileo had unwittingly flown through a Europa plume more than 20 years before anyone thought to look for one. Each of these detections, taken individually, is at or near the limits of the instruments that produced it. Roth's UV emissions were faint. Sparks's transit absorptions were subtle. The Galileo magnetic signatures were short and required sophisticated reanalysis to identify. None of them would, on their own, constitute a definitive detection. Together, they build a suggestive case. But suggestive is not the same as confirmed. And then JWST looked, the most sensitive infrared telescope ever built, with the spectral resolution to detect trace gases at concentrations far below what Hubble could see, specifically searched for evidence of water plumes during its November 2022 observation of Europa. Villanueva's team probed for fluorescence emissions from water, methane, ethane, methanol, and carbon monoxide. Their result was unambiguous. No plume activity detected. Strict upper limits on mass ejection rates that would have caught anything comparable to the features Hubble reported. This does not necessarily mean the plumes do not exist. If they are truly episodic, erupting intermittently and unpredictably, then the odds of catching one during a single observation are not great. Europa's plumes, if real, might erupt only occasionally, perhaps driven by tidal stresses that peak at certain points in Europa's orbit, or triggered by geological events that we cannot predict. But the JWST null result does mean that Europa's plumes, as of early 2026, remain in the category of strongly suggested but not definitively confirmed, and that distinction matters enormously. On Enceladus, there is no ambiguity, none at all. Saturn's 6th largest moon, only about 500 kilometers in diameter, roughly the width of Arizona, has been erupting water into space continuously since at least 2005, when the Cassini spacecraft first observed jets of water vapor and ice particles shooting from fractures near the South Pole. Cassini flew through those plumes repeatedly over its 13-year mission, directly sampling the material with its mass spectrometer and dust analyzer. This was not remote detection. This was not inference. This was a spacecraft physically tasting ocean water that had been launched into space through cracks in the ice. And what Cassini found in that water reads like a wish list for astrobiology. Molecule hydrogen, detected by Waite and colleagues and published in Science in 2017, at concentrations indicating ongoing hydrothermal reactions on the seafloor. Silica nanoparticles, reported by Hsu and colleagues in Nature in 2015, pointing to seafloor temperatures of at least 90 degrees Celsius, hot enough for vigorous water rock chemistry, complex macromolecular organic compounds with masses above 200 atomic mass units, found by Postberg and colleagues and published in Nature in 2018, the kind of large organic molecules that on Earth are associated with biological processes or with the prebiotic chemistry that leads to biology. And in 2023, Postberg's group delivered perhaps the most remarkable result of all. Phosphorus, detected in the ice grains erupted from Enceladus, had concentrations 100 to 1,000 times higher than in Earth's oceans. Published in Nature, the phosphorus detection means Enceladus's ocean contains every single element that life as we know it requires: hydrogen, carbon, nitrogen, oxygen, sulfur, and phosphorus, the complete set. No other world beyond Earth has that confirmed chemical inventory. So why are we not sending every available spacecraft to Enceladus instead of Europa? Because Europa has advantages that Enceladus cannot match, and they are the kind of advantages that matter on timescales of billions of years. First, size. Europa's ocean is vastly larger. By the most commonly cited estimates, Enceladus's ocean is comparable in volume to Lake Superior, roughly 12,000 cubic kilometers. Europa's is 3 billion cubic kilometers. That is a difference of 5 orders of magnitude. A bigger ocean means a larger potential habitat, more dissolved chemicals, more diverse environments, and more room for whatever processes initiate and sustain biology. Second, time. Europa's ocean has almost certainly existed for roughly 4.5 billion years, maintained by the stable Laplace resonance that keeps Europa's orbit slightly elliptical and the tidal heating flowing. On Earth, life appeared relatively quickly once conditions became suitable, perhaps within a few 100 million years of the planet's formation. If Europa's ocean has been liquid for 4.5 billion years, biology has had comparable time to emerge and evolve. Enceladus's long-term tidal heating budget is less certain. Some models suggest the current level of activity may be geologically recent, perhaps only 100 million years old, which would mean less time for prebiotic chemistry to do its work. Third, energy diversity. Europa benefits from intense radiation-driven surface chemistry that produces oxidants from potential hydrothermal activity at the seafloor and from tidal heating throughout the ice shell. This means the ocean could be energized from both above and below. Enceladus has confirmed hydrothermal activity but lacks the intense radiation environment because Saturn's magnetosphere is far weaker than Jupiter's, and Enceladus orbits at a greater relative distance from it. Fourth, and this is admittedly more speculative, Europa's ocean contacts rock along a much larger surface area. A bigger moon means more seafloor, more potential sites for water rock interaction, more chemical niches. The total energy and nutrient flux from Europa's interior to its ocean, even if the seafloor is less active per unit area than Enceladus's, could be higher in absolute terms, simply because there is so much more seafloor. Enceladus has the confirmed chemistry. Europa has the scale, the time, and the energy diversity. Both are compelling. Both deserve missions. But the practical consideration that tipped the scales, at least for now, is that Europa Clipper is already on its way. The Enceladus Orbilander, a proposed NASA flagship mission to orbit and eventually land on Enceladus, remains a concept without funding. The politics and economics of planetary exploration are as much a part of this story as the science. And right now, Europa has the spacecraft. But before that spacecraft, before Europa Clipper, before JWST, before Hubble, there was a stretch of exploration history that built everything we currently know about this moon. And that history begins with a few blurry pixels. Pioneer 10 captured the first spacecraft image of Europa during its December 3rd and 4th, 1973 flyby of Jupiter. The image shows almost nothing recognizable, just a bright, slightly resolved dot against the blackness. But it confirmed Europa's existence as a physical body, a world you could take a picture of, not just a point of light tracked through a telescope. 6 years later, Voyager 1 changed everything. During its March 5, 1979 Jupiter flyby, passing Europa at a distance of about 733,760 kilometers, Voyager revealed something nobody expected. Europa's surface was covered in a network of dark intersecting lines, like veins on the back of a hand, stretching across a bright, almost featureless white sphere. There were essentially no impact craters on a world orbiting a planet in the most debris-rich region of the solar system, a world where you would expect to see the accumulated scars of billions of years of bombardment. The surface was almost pristine. The absence of craters was the first major clue. It meant the surface was young. Something was erasing craters, resurfacing the moon, replacing old terrain with new. And the only mechanism that could do this on the scale required was liquid water. Scientists first suspected a subsurface ocean in 1979 based on these Voyager images. The hypothesis was speculative but physically reasonable, and it set the direction for the next 50 years of Europa research. Voyager 2 passed Europa on July 9, 1979, at a closer range of 205,720 kilometers, providing the first detailed images. The linear features resolved into complex ridge systems, double-ridged lineae with central troughs, cycloidal cracks that traced out scalloped arcs across the surface. One scientist, looking at the images for the first time, noted that the lines might have been painted on with a felt marker. It was an eerily apt description. The lines were too regular, too geometric, too globally organized to be random fractures. They spoke of a surface under systematic stress, a world being pulled and squeezed by forces acting from within. But Voyager was a flyby mission. It saw Europa for a brief window and then moved on, leaving behind tantalizing images and unanswered questions. The spacecraft that would transform Europa from a curiosity into a destination took 16 years to arrive. Galileo launched on October 18, 1989, and entered Jupiter orbit on December 7, 1995. Over the next 5 years, it conducted 11 targeted flybys of Europa, approaching as close as approximately 200 kilometers during the E12 encounter on December 16, 1997. At that distance, its camera resolved surface features down to 6 meters per pixel, revealing the chaos terrain, the ice rafts, the ridge systems, and the geological complexity that had only been hinted at by Voyager. But Galileo operated under a crippling handicap. Its high-gain antenna, the large umbrella-shaped dish that was supposed to relay data back to Earth at high speeds, failed to fully deploy after launch. The ribs of the antenna stuck, probably due to friction caused by lubricant loss during the years Galileo sat in storage after the Challenger disaster delayed its launch. Without the high-gain antenna, Galileo was forced to transmit data through its low-gain antenna at a tiny fraction of the planned data rate. The mission returned roughly 2% of the imaging data it was designed to collect. Imagine spending more than a decade building and flying a spacecraft to Jupiter, conducting 11 close flybys of the most intriguing moon in the solar system, and getting back only 1/50th of the pictures. Despite this limitation, Galileo's science return was extraordinary. The magnetometer data that confirmed Europa's ocean, the NIMS spectra that detected surface salts, the images of chaos terrain that revealed the geological pipeline from interior to surface, the close-up views of Connemara chaos that showed the jigsaw puzzle of ice rafts. Almost everything we knew about Europa before the JWST era came from Galileo. Operating with one arm tied behind its back, the mission ended on September 21st, 2003, when Galileo was deliberately plunged into Jupiter's atmosphere to prevent any possibility of the spacecraft eventually crashing into Europa and contaminating it with Earth microbes. That act of planetary protection, destroying a billion-dollar spacecraft to protect a world we had only begun to explore, tells you something about how seriously scientists take Europa's potential for life. Between Galileo's demise and the JWST era, Europa's science continued through Earth-based telescopes and Hubble. Cassini, on its way to Saturn, observed Europa only remotely from a distance of about 9.7 million kilometers during its December 2000 Jupiter gravity assist, detecting atmospheric glows during eclipses, but contributing nothing significant to Europa-specific science. The real progress came from the salt and plume detections already discussed, Hans irradiation experiments, Trumbo's sodium chloride confirmation, and Roth's tentative plume observations. But there was one more spacecraft that contributed something critical, almost as an afterthought. Juno, which entered Jupiter orbit in July 2016, primarily to study Jupiter itself, was never designed for Europa science. Its instruments are tuned to Jupiter's atmosphere, magnetic field, and interior. But during a close approach to Europa, on September the 29th, 2022, Juno's microwave radiometer was pointed at the moon, and it delivered the ice shell thickness measurement that had eluded every previous attempt, 29 plus or minus 10 kilometers, a number that landed like a verdict in the great thickness debate, and a number that Europa Clipper will refine with its own ice-penetrating radar within a few years of arriving at Jupiter. The history of Europa exploration is a story of instruments pushed beyond their design limits, of data squeezed for every last photon of information, of scientists spending decades assembling a picture from fragments. And the picture they have assembled, while still incomplete, is remarkable. An ocean larger than all of Earth's water combined, hidden beneath an ice shell 3.5 Everests thick, carbon from that ocean reaching the surface through geological pipelines that operate on timescales of days. Sodium chloride salt, implying hydrothermal water rock interactions on the seafloor. Radiation-driven oxidant production on the surface that could, if it reaches the ocean, provide chemical energy for life. An ice shell that is simultaneously a barrier protecting the ocean from space and a conduit through which chemistry might flow. Every piece of this picture is extraordinary on its own. Together, they form the most compelling case for a habitable environment beyond Earth that planetary science has ever assembled. But the word Habitable is doing heavy lifting here, and it does not mean what many people think it means. Habitable means the conditions could support life. It does not mean life is there, and the gap between could and is may be the deepest question in all of science. To bridge that gap, or at least to narrow it, we need a spacecraft designed not to glimpse Europa in passing, not to observe it from millions of kilometers away, not to infer its properties from a few minutes of telescope time, but to study it systematically, repeatedly, intimately, with instruments built specifically to answer the questions that 3 decades of exploration have sharpened to fine points. That spacecraft left Earth on October 14th, 2024. And the story of how it nearly did not make it off the ground is a story about transistors, radiation, and a desperate 4-month scramble that pushed 3 of NASA's largest research centers to their limits. Europa Clipper is the largest planetary science spacecraft NASA has ever built, with a total life cycle cost of approximately $5.2 billion and a spacecraft mass of roughly 6,000 kilograms, half of which is propellant. It represents the single biggest bet the agency has placed on the search for life beyond Earth. It launched aboard a SpaceX Falcon Heavy in fully expendable configuration from Kennedy Space Center's Launch Complex 39A at 12:06 p.m. Eastern Daylight Time. The rocket that carried it to space was the same type that normally lands its boosters back on Earth for reuse. But Europa Clipper was heavy enough and the trajectory demanding enough that all 3 cores were expended. Nothing came back. The spacecraft carries 9 science instruments and a gravity science experiment, and understanding what those instruments can do is essential to understanding what Europa Clipper can actually answer, because this is a habitability assessment mission, not a life detection mission. And that distinction matters more than almost any headline conveys. Start with REASON, which stands for Radar for Europa Assessment and Sounding, Ocean to Near Surface. This is a dual-frequency ice-penetrating radar operating at 9 MHz and 60 MHz, designed to see through Europa's ice shell to a depth of up to 30 kilometers. Think about that. If the ice shell is 29 plus or minus 10 kilometers thick, REASON can potentially see all the way through it. It will create 3-dimensional images of the ice shell's internal structure, revealing layers, fractures, voids, subsurface lakes, and, if conditions are favorable, the ice-ocean interface itself. The principal investigator is Donald Blankenship at the University of Texas at Austin, who has spent decades using similar radar systems to map ice sheets in Antarctica. The technology is proven. Seeing through ice from orbit is something we know how to do. Doing it at Europa, through ice that may be orders of magnitude deeper than Antarctic ice sheets, and in a radiation environment that introduces enormous noise, is the hard part. The Europa Imaging System, EIS, consists of wide-angle and narrow-angle cameras with 8-megapixel CMOS sensors capable of achieving resolution down to 0.5 meter per pixel at closest approach. That is 240 times sharper than the best Galileo images from a comparable distance. EIS will map 90% of Europa's surface at 100-meter resolution, finally giving scientists a complete global picture of the surface geology that Galileo could only glimpse in fragments. MISE, the Mapping Imaging Spectrometer for Europa, operates in the infrared between 0.8 and 5.0 micrometers, mapping water, ices, salts, organics, and thermal hotspots at 25 meters per pixel, where JWST saw Europa as a blob of roughly 320 by 320 kilometers per pixel. MIS will see individual ridges, individual blocks of chaos terrain, individual geological features. If there are specific spots on the surface where ocean chemistry is particularly concentrated, MIS will find them. Themis, the Europa Thermal Emission Imaging System, is a 3-band thermal imager covering 7 to 80 micrometers. Its purpose is to detect heat. If warm water is near the surface, Themis can see it. If there are active vents or cryovolcanic features producing thermal anomalies, Themis can see those too, at a resolution of 1 to 10 meters. The principal investigator is Philip Christensen at Arizona State University, one of the most experienced thermal imaging scientists in planetary exploration. AMASPEX, the mass spectrometer for planetary exploration, may be the single most important instrument on the spacecraft for the habitability question. It is a multi-bounce time of flight mass spectrometer with a mass resolution of approximately 25,000 and sensitivity down to parts per trillion. Those numbers mean it can detect and identify trace gases in Europa's extremely thin atmosphere or in any plume material the spacecraft might encounter, with a specificity that is, according to the mission team, hundreds of times finer than anything previously flown to space. From trace atmospheric gases alone, MASPEX can potentially determine the ocean's pH, its temperature, its free energy content, and the types of chemical reactions occurring within it. It can do this without ever touching the ocean, simply by sniffing the vanishingly thin wisps of gas that escape from below. SUDA, the surface dust analyzer, is an impact ionization mass spectrometer designed to catch and analyze tiny solid particles ejected from Europa's surface by micrometeorite bombardment. These particles are microscopic, launched into space by the constant rain of tiny impactors hitting Europa, and they carry the chemical signature of whatever surface material they originated from. SUDA is sensitive enough to detect biosignatures in less than a single bacterial cell's worth of material. If something in Europa's ocean produces molecules that reach the surface and get lofted into space by micrometeorite impacts, SUDA can potentially identify those molecules even in vanishingly small quantities. Europa UVS, the ultraviolet spectrograph, searches for plumes using the same ultraviolet technique that produced Hubble's 2012 detection, but it does so with far greater sensitivity and from far closer range. If Europa's plumes are real and intermittent, Europa UVS is the instrument most likely to catch them in the act during one of the spacecraft's 49 flybys. The Europa Clipper magnetometer, ECM, consists of 3 fluxgate magnetometers mounted on an 8.5-meter boom extending from the spacecraft body. The boom keeps the magnetometers away from the spacecraft's own magnetic interference, and the 3 sensors at different positions allow the team to subtract any residual spacecraft field. Over 49 flybys, ECM will measure Europa's induced magnetic field from a range of geometries far more diverse than anything Galileo achieved, constraining the ocean's depth, salinity, and the ice shell thickness with unprecedented precision. Kjellsen's intellectual descendant indeed, and PIMS, the plasma instrument for magnetic sounding, carries 4 Faraday cup detectors to measure the charged particle environment around Europa. This might sound redundant with the magnetometer, but it serves a critical function. Jupiter's magnetospheric plasma creates its own magnetic distortions that can mimic or mask the ocean's induced field. PIMS measures the plasma directly so the magnetometer team can subtract its contribution, isolating the signal from the ocean. Without PIMS, the magnetometer data would be ambiguous. With PIMS, the ocean's signal can be extracted cleanly. The mission plan calls for 49 close flybys of Europa at altitudes as low as 25 kilometers, about 16 miles, which is lower than most commercial aircraft fly above Earth's surface. But Europa Clipper will not orbit Europa. It will orbit Jupiter, swooping in for brief encounters with the Moon before retreating to safer orbital distances. The reason is radiation. Jupiter's magnetosphere is so intense, and Europa sits so deep within its radiation belts that each close flyby exposes the spacecraft to roughly 12 hours of punishing bombardment. By orbiting Jupiter on a wide, elliptical path, the spacecraft limits its time in the worst radiation zones to those brief flyby windows, spending the weeks between encounters in regions where the radiation is manageable. The radiation vault is the engineering solution that makes this possible. Nearly all of Europa Clipper's electronics are housed inside a structure with walls of 9.2 millimeters of aluminum zinc alloy, designed to absorb and attenuate the radiation to levels the electronics can survive. Over the course of the full mission, the total radiation dose the electronics will absorb is expected to reach approximately 2.8 megarads. To put that in perspective, a lethal dose for a human is about 400 rads. The electronics inside the vault will absorb 7,000 times that amount over the mission's lifetime. And this is where the story nearly fell apart. In May of 2024, roughly 5 months before the planned October launch, engineers at JPL discovered a problem with certain transistors manufactured by Infineon Technologies, specifically metal oxide semiconductor transistors, roughly 1,500 of them, embedded throughout the spacecraft's electronics, including many sealed inside the radiation vault, where they could not be accessed or replaced. Testing revealed that these transistors were failing at lower radiation doses than their specifications indicated, due to an undisclosed change in Infineon's manufacturing process. The discovery was described by people involved as eliciting a howl of terror. The entire mission timeline hung in the balance. If the transistors could not survive the radiation environment, Europa Clipper's electronics would fail before the science mission was complete. Replacing them was essentially impossible because they were integrated into circuit boards that were themselves integrated into instruments that were themselves sealed inside the vault. This was not a problem you could fix with a screwdriver. What followed was a 4-month, around-the-clock testing campaign across 3 of NASA's largest research centers, JPL, the Applied Physics Laboratory at Johns Hopkins, and Goddard Space Flight Center. Engineers subjected identical transistors to simulated Jupiter radiation environments, tested them at various temperatures, measured their degradation curves, and looked for any mechanism that might allow them to survive longer than the initial tests suggested. They found one: thermal annealing. When the transistors warm up, the radiation damage partially heals. The crystal structure of the semiconductor, distorted by radiation-induced defects, relaxes and recovers some of its original properties when the temperature rises, even modestly. And the mission profile provides exactly this opportunity. Between each of the 49 flybys, the spacecraft spends 20 or more days in the outer reaches of its Jupiter orbit, far from the worst radiation zones during which the electronics warm up relative to their temperatures during close approach. This warming period allows the transistors to partially anneal, recovering enough function to survive the next flyby. The analysis showed that with the annealing effect accounted for, the transistors would survive the full mission. NASA cleared Europa Clipper for launch on September 4, 2024, just 6 weeks before the October 14th window. If the problem had been discovered even a few months later, or if the annealing solution had not worked, the mission could have been delayed by years at a cost of hundreds of millions of additional dollars. As of February 2026, Europa Clipper is well on its way. It completed a Mars gravity assist on March 1st, 2025, passing 884 kilometers above the Martian surface, just 2 kilometers from the target altitude. During the Mars flyby, the Reason radar team tested their instrument against Martian terrain, getting real-world calibration data that will help them interpret Europa's ice shell. In November 2025, the spacecraft observed interstellar comet 3I/Atlas with its ultraviolet spectrograph, a bonus science observation that demonstrated the instrument's capabilities. The next major milestone is an Earth gravity assist on December 3, 2026. Jupiter orbit insertion is scheduled for April 11, 2030, with the first Europa science flyby expected in spring of 2031, and science operations continuing through approximately 2034. 5 years from now, Reason will be sending radar pulses through Europa's ice shell and listening for echoes from the ocean below. The magnetometer will be measuring the induced field from geometries Galileo never achieved. Our mass specs will be sniffing the atmosphere for trace gases that reveal ocean chemistry. And if, during any of those 49 flybys, a plume happens to be erupting, SUDA and mass specs will fly directly through it, tasting ocean water for the first time. But here is what Europa Clipper will not do. And this is perhaps the most important misconception to correct. It will not land. It will not drill. It will not deploy a submarine. It will not put a camera in the ocean. It will make 49 close flybys from Jupiter orbit, gathering data remotely. And then it will be done. A Europa lander concept exists. NASA's Jet Propulsion Laboratory has produced detailed design studies for a spacecraft that could touch down on the surface, melt, or drill through the ice and search for direct evidence of life. But that mission is unfunded, existing only on paper, with no timeline for development. The jump from flyby to landing, from habitability assessment to life detection, is a technological and financial leap that has not yet been made. And even the question Europa Clipper can answer, whether the ocean is habitable, carries a profound ambiguity. If the instruments find conditions consistent with habitability, warm liquid water, carbon chemistry, energy gradients, the right salts and nutrients, it will mean that life could exist in Europa's ocean. Not that it does. The gap between could and does is the gap between chemistry and biology, between having all the ingredients laid out on the counter and actually baking the cake. It is the gap that defines the search for life beyond Earth. And it is a gap that no spacecraft currently built or planned is designed to close with certainty for Europa. So the question this entire story has been circling around, the question that the JWST data sharpened and Europa Clipper was designed to approach, but perhaps not fully answer, remains open. Europa has the water, It has the carbon. It probably has the energy. It has the salts. It has the rock contact. It has had 4.5 billion years. Everything we can observe or infer points toward habitability. But there is always a but. The ice shell might be too thick for surface oxidants to reach the ocean in meaningful quantities. The seafloor might not be geologically active enough to provide the chemical energy a biosphere would need. The plumes that could give us free samples of ocean water might not exist, or might erupt so rarely that Europa Clipper misses them entirely across all 49 encounters. The salinity of the ocean spans 5 orders of magnitude across published models, and at the extremes of that range, the water could be so briny or so dilute that the chemistry of life as we understand it simply does not work. Phosphorus and sulfur, 2 of the 6 elements biology requires, have not been detected at Europa at all. They are expected from formation models. They are assumed from what we know about the composition of the outer solar system, but expected and assumed are not detected and confirmed. And the history of Europa science is littered with assumptions that later turned out to be wrong. Remember the magnesium sulfate ocean? For nearly 20 years, the consensus held that Europa's surface salts were Epsom salt, that the ocean was dominated by sulfate chemistry, that its geochemistry looked nothing like Earth's. That consensus was built on real data from a real instrument on a real spacecraft, and it was wrong, or at the very least profoundly incomplete, because the instrument could not see what was actually there. Sodium chloride was invisible in the infrared. The Galileo NIMS spectrometer was looking for salts with the wrong tool, like trying to read a book in a dark room with a flashlight that only emitted ultraviolet. The book is there. Your light just cannot illuminate it. How many other critical properties of Europa's ocean are we currently unable to see because we are looking with the wrong instruments, at the wrong wavelengths, from the wrong distance? This is not a rhetorical question. It is the operational uncertainty that drives the entire Europa Clipper mission. The spacecraft carries 9 instruments, not because 9 is a nice number, but because each instrument sees Europa differently, at different wavelengths, in different physical modalities, from different perspectives. The hope is that by looking at the same moon through 9 different lenses simultaneously, the blind spots of each instrument will be covered by the strengths of another. And this is where the biographical threads of this story begin to converge on a single moment. Margaret Kivelson, 97 years old, who fought through gender exclusion and decades of delayed recognition to make the measurement that proved Europa's ocean exists, is still guiding the magnetometer that will determine what that ocean is actually like. Robert Pappalardo, who has devoted roughly 30 years of his career to Europa, from the first Galileo images through the agonizing decades of mission cancellations and restarts to the day he watched Clipper leave the launch pad as the mission's project scientist, Samantha Trumbo, whose dissertation on Europa produced 2 of the most consequential discoveries in the field, the sodium chloride and the JWST carbon dioxide, and who is now an assistant professor continuing the work. Kevin Hand, whose vacuum chamber experiment cracked the irradiated salt mystery, and whose book Alien Oceans articulated for a general audience what had previously lived only in specialist journals. These are people who have bet their professional lives on a frozen moon orbiting a gas giant 5 times farther from the sun than we are. They have done so not because they believe life is there, though some of them suspect it might be, but because the question of whether life could be there is among the most profound questions science has ever had the tools to approach. And in spring of 2031, when Europa Clipper makes its first close flyby and the data begins streaming back across the 550 million to 900 million kilometer gulf between Jupiter and Earth, arriving 33 to 54 minutes after transmission, because even light takes that long to make the journey, the answers those scientists have spent decades working toward will finally begin to arrive. Whether those answers reveal a habitable ocean or a sterile one, whether they confirm the optimists' models or the skeptics' cautions, whether they find plumes or silence, warmth or cold, complex chemistry or simple, the result will reshape our understanding of where life can take hold. Because if Europa's ocean is habitable, it means habitable oceans can form and persist under ice shells on moons orbiting gas giants. And the galaxy is full of gas giants with icy moons. The implication would extend far beyond one moon of Jupiter. Robert Pappalardo has said it as clearly as anyone. Icy ocean worlds could be the most common habitat for life, not just in our solar system, but throughout the universe. That is the scale of what is at stake. Not one moon, not one ocean. The fundamental architecture of where life exists. But we are getting ahead of ourselves, because before we can weigh what Europa Clipper's findings might mean, we need to confront something uncomfortable. We need to talk about what the public gets wrong about Europa, why those misunderstandings persist, and what the actual boundaries of our knowledge look like when you strip away the headlines and the hype. And then we need to return to where we started, to that JWST observation on a November evening in 2022, and ask what it truly means for the question that has driven 50 years of exploration. The carbon came from the ocean, but what does the ocean actually look like if you could somehow stand on its floor and look up through 150 kilometers of water and ice toward a sky you would never see? What would you find down there? Nobody knows, not yet, but in 4.5 years, we will have the best shot at an answer that humanity has ever had. Let us talk about what people get wrong, because the misconceptions about Europa are not trivial misunderstandings. They are errors that distort public expectations, inflate what Europa Clipper can deliver, and set the stage for disappointment when the reality of this mission turns out to be slower, more ambiguous, and more scientifically cautious than the headlines suggest. The first and most widespread misconception is that life has been detected on Europa. It has not. Nothing remotely close to a life detection has occurred. What has been detected is carbon dioxide on the surface, sodium chloride on the surface, hydrogen peroxide on the surface, and an induced magnetic field consistent with a subsurface ocean. These are ingredients and conditions. They are not life. They are not even direct evidence of life. They are evidence that Europa's ocean might be the kind of place where life could exist. The distinction matters because the language of science communication often blurs it. Headlines reading, "NASA finds key ingredient for life on Europa," or "Ocean world Europa moves closer to habitability," are technically accurate but psychologically misleading. They create a ratchet effect in public perception, where each new discovery feels like another step closer to confirmation, as if there were a progress bar slowly filling toward the moment scientists announce alien microbes. That is not how this works. Each discovery constrains the probability space. It narrows the range of possible conditions in the ocean, but it does not accumulate toward a threshold beyond which life is confirmed. Life detection requires detecting life, actual biological molecules, metabolic byproducts, cellular structures, or some other unambiguous signature of biology. Nothing less will do. Europa Clipper is explicitly a habitability assessment mission, not a life detection mission. The mission's primary science objectives, as stated in the formal mission documentation, are to confirm the existence of Europa's ocean, characterize its ice shell, investigate the composition and geology of the surface, and assess whether the conditions necessary for life exist. Notice what is absent from that list. Finding life. The mission was designed, funded, and built to answer whether life could be there, not whether it is. Could Europa Clipper detect life accidentally? If life happens to be producing obvious chemical signatures that reach the surface or atmosphere? Possibly. Amaspex's parts per trillion sensitivity and SUDA's ability to identify biosignatures in less than a single cell's worth of material are capabilities that could, in principle, pick up biological signals if they exist in the right places at the right concentrations. But the mission was not optimized for this, and any such detection would be contested, debated, and subjected to years of alternative hypothesis testing before the scientific community would accept it. If Europa Clipper finds something that looks biological, the first response will not be celebration. It will be an exhaustive search for non-biological explanations. The second major misconception is about plumes. People frequently confuse Europa with Enceladus, attributing confirmed geyser activity to the wrong moon. Enceladus has confirmed robust, permanent plumes that Cassini flew through dozens of times over more than a decade. Europa has tentative, episodic, unconfirmed plume detections that appear in some observations and vanish in others, with the most powerful telescope ever built failing to see them at all during its observation. The difference is not a matter of degree, it is a difference in kind. Enceladus's plumes are a confirmed geological feature. Europa's plumes are a hypothesis with supporting but inconclusive evidence. This confusion has practical consequences. Many popular articles describe Europa Clipper as a mission designed to fly through Europa's plumes and sample ocean water, as though this were the primary science plan. It is not. Plume sampling is a contingency objective, something the spacecraft is capable of doing if a plume happens to erupt during one of the 49 flybys. The mission is designed to achieve its primary science goals entirely through remote sensing and atmospheric sampling, whether or not any plumes are ever detected. If plumes happen, MASPX and SUDA will take full advantage. If they do not, the mission is not a failure. The third misconception concerns the telescope. When JWST detected CO2 on Europa, many people assumed the telescope was somehow seeing into or through Europa's ice shell, imaging the ocean itself. It was not. JWST performs surface spectroscopy. It analyzes reflected sunlight that has bounced off Europa's surface and passed through the thin atmosphere, identifying chemical compounds by their characteristic absorption patterns at specific wavelengths. The telescope sees the surface and only the surface at a spatial resolution of roughly 320 by 320 kilometers per pixel. That is not fine enough to see individual geological features. Europa appeared to JWST as a disk a few pixels across. The chemistry JWST detected is real, and the conclusions are sound, but the telescope provides indirect evidence about ocean chemistry, not images of the ocean. The fourth misconception is about what the ocean is like. Popular depictions, and some unfortunately misleading illustrations, released even by science institutions, sometimes show Europa's ocean as a warm, brightly lit underwater landscape, dotted with hydrothermal vents billowing dark mineral plumes into the water, surrounded by thriving ecosystems of alien organisms. Every element of this image is either wrong or highly uncertain. The ocean is dark, completely dark. No sunlight penetrates 29 kilometers of ice. Whatever light exists would be limited to bioluminescence, if organisms capable of it exist, or the faint thermal glow of extremely hot rock, if hydrothermal vents are present. The ocean temperature sits near the freezing point of water, not the steaming temperatures depicted in some illustrations. The January 2026 Burns study in Nature Communications raised real questions about whether the seafloor is even geologically active enough to produce the dramatic vent systems that artists love to draw. The ocean may be cold, dark, still, and chemically quiet. That would not mean it is lifeless. Life thrives in cold, dark, chemically quiet environments on Earth. But the popular image of an underwater volcano park teeming with alien shrimp is not supported by the current evidence. The fifth misconception, and perhaps the most subtly damaging, is about what something moving under the ice means when it appears in headlines. Several news articles in recent years have used language suggesting that scientists detected movement beneath Europa's ice surface, with wording that easily implies biological activity. In every case, the underlying science describes geological processes, tectonic shifting of ice blocks, thermal convection within the ice shell, possible diaperic upwelling of warm ice, cryovolcanic activity. These are physical, geological, chemical processes. They involve the movement of ice, rock, water, and dissolved materials through gravitational, thermal, and tidal forces. They do not involve organisms. The movement is real, geologically significant, and fascinating in its own right. But it is the movement of a world's interior, not the movement of anything alive. Now, having stripped away the misconceptions, let us rebuild the picture from what is actually known and actually uncertain, because the honest version of Europa's habitability case, the version without the hype, is in some ways more interesting than the exaggerated one. Uncertainty is not a weakness. It is the map of where discoveries remain to be made. Here is what we know with high confidence. Europa has a global subsurface ocean. The Galileo magnetometer data requires a conductive global layer, and the most physically plausible conductor is salt water. This is not proven in the absolute sense of having touched or sampled the water, but within the framework of electromagnetic theory. The case is about as strong as indirect evidence gets. Juno's microwave radiometer measurement places the ice shell at approximately 29 kilometers thick, which constrains the ocean to begin at that depth, give or take 10 kilometers, and extend to somewhere between 60 and 150 kilometers below the surface. The total water volume is between 2 and 3 times that of Earth's oceans. We know with high confidence that the ocean contains carbon. The JWST carbon dioxide detection on the surface, concentrated in chaos terrain with co-located sodium chloride with no alternative source pathway that survives scrutiny, establishes that carbon from the ocean reaches the surface. The isotope ratio is consistent with solar system sources. The carbon is real. Its ocean origin is robust. We know with high confidence that Europa's surface chemistry includes radiation products that are potentially useful for biology. Hydrogen peroxide has been detected repeatedly by Galileo, by Keck, and by JWST. The concentrations are well established on the leading hemisphere. The 2 to 3-fold enhancement of peroxide production in the presence of CO2, demonstrated in laboratory experiments by Wu and colleagues, is a measured physical effect. Surface radiation chemistry is real and active. We know with moderate confidence that the ocean contains sodium chloride and that this implies some form of water-rock interaction, possibly hydrothermal. The spectroscopic detection is solid. The irradiation physics linking NaCl to Europa's surface colors is demonstrated in the laboratory. The inference that NaCl indicates hydrothermal processing is based on well-understood terrestrial geochemistry. The main uncertainty is whether the hydrothermal activity is current or relict, a question the 2026 Burn study highlighted. We know with moderate confidence that the chaos terrain serves as a geological pipeline from the ocean to the surface. The concentration of endogenous materials in chaos regions, the crystalline ice discovery indicating resurfacing on timescales of days, the co-location of multiple ocean-derived compounds, all point to active exchange. What we do not know is the efficiency, selectivity, and directionality of that pipeline. Material clearly moves up. Whether it moves down at rates sufficient to deliver meaningful quantities of surface oxidants to the ocean is unestablished. And we know with low confidence, or more honestly, we do not know at all, several things that matter enormously. The ocean's salinity. Published estimates span 5 orders of magnitude, from nearly fresh water to brines several times saltier than the Dead Sea. The pH, which determines which chemical reactions are thermodynamically favorable. The redox chemistry, which determines the energy available for metabolisms. The phosphorus and sulfur content, both essential for all known biology and both undetected at Europa. The rate of oxidant delivery to the ocean. The level of current seafloor geological activity. The presence or absence of hydrothermal vents. The internal structure of the ice shell, whether it contains subsurface lakes, convection cells, or fracture networks that facilitate material transport. That is the honest scorecard. It is impressive, and it is humbling. Impressive because no other world beyond Earth has this combination of liquid water, confirmed ocean-derived carbon, energy sources, and rock contact. Humbling because the things we do not know about Europa's ocean could easily be the things that determine whether it is habitable or not. Salinity is a good example of how a single, poorly constrained property can swing the entire habitability assessment. At very low salinities, the ocean might lack the dissolved mineral content needed for complex chemistry. At very high salinities, the water activity drops to a point where many biological processes become thermodynamically impossible. Earth's saltiest environments, like Don Juan Pond in Antarctica's Wright Valley, with a salinity of roughly 40%, are essentially sterile. Not because the water is too cold or too dark, but because the water activity is too low. The molecules of water are so busy hydrating dissolved ions that they are not available for the biochemical reactions that life requires. If Europa's ocean sits at the high end of published salinity estimates, this same problem could apply. But we do not know the salinity. The magnetometer constrains the conductivity, not the composition. A conductivity of 0.06 Siemens per meter can be achieved by many different salt compositions at many different concentrations, until Europa Clipper's magnetometer measures the induction signal from 49 different geometries, and until MSPX sniffs the trace atmosphere for dissolved gases that correlate with salinity. The ocean's salt content will remain a placeholder in every habitability model, and salinity is just one of many unknowns. The pH question is similarly consequential. On Earth, life exists across a pH range from about 0 in extremely acidic mine drainage to about 13 in highly alkaline soda lakes. But the sweet spot for complex biochemistry, the range where the largest diversity of metabolic strategies operates, is roughly pH 5 to 9. Europa's ocean pH is unknown. It depends on the balance between acidic inputs, such as carbon dioxide dissolved in the water, and alkaline inputs, such as minerals leached from the seafloor. If the ocean is in contact with fresh basaltic rock and the water-rock reactions are vigorous, the pH could be moderately alkaline, similar to lost city-style hydrothermal systems on Earth, which is excellent for certain types of prebiotic chemistry. If the water-rock reactions are sluggish and CO2 is the dominant dissolved species, the ocean could be weakly acidic, which favors different chemistry entirely. Different pH means different available chemical reactions, different metabolic possibilities, and a different answer to the habitability question. The redox chemistry problem is perhaps the most critical of all, and it connects directly to the radiation paradox we discussed earlier. Life as we know it requires a chemical energy gradient, a disequilibrium between oxidized and reduced species that organisms can exploit. On Earth's surface, the dominant disequilibrium is between atmospheric oxygen, produced by photosynthesis, and reduced carbon compounds in food. In the deep ocean, the disequilibrium is between oxidants in seawater and reduced chemicals, hydrogen sulfide, hydrogen, methane, emerging from hydrothermal vents. Europa's ocean could have both sides of this equation. The surface radiation chemistry produces oxidants. The seafloor water-rock interactions could produce reductants like hydrogen. If both reach the ocean, you have a chemical gradient. Life could exploit it, but the two sides of the equation face different transport challenges. Oxidants need to get from the surface through 29 kilometers of ice to the ocean. Reductants need to get from the rocky mantle into the ocean water. The first pathway is uncertain because we do not understand ice shell transport well. The second pathway is uncertain because we do not know how geologically active the seafloor is. The 2026 Burns study hits this problem directly. If their models are correct and Europa's seafloor is relatively quiescent, then the reductant side of the equation is weaker than previously assumed. The ocean would then be more dependent on the oxidant side, which requires surface-to-ocean transport through the ice shell. And if that transport is inefficient, the ocean could be energy poor, not dead, necessarily. Life can persist at extremely low energy fluxes, but the biosphere would be thin, sparse, limited, something more like the deep subsurface biosphere of Earth's continental crust, where microbial cells sit in rock fractures, metabolizing at rates so slow they divide once every few thousand years. Then, like the teeming ecosystems around black smokers on the mid-ocean ridge. This is not a pessimistic scenario. It is a realistic one, and it matters because it sets expectations for what Europa Clipper might or might not find. If Europa's biosphere, if it exists, is sparse and slow, its chemical footprint may be vanishingly faint. Aspects might detect trace gases that are consistent with biology, but also consistent with abiotic chemistry. SUDA might catch particles that contain organic molecules that could be biological or could be produced by non-biological processes in the ice shell. The ambiguity could persist even after decades of data analysis. This is worth sitting with for a moment. We are building a $5.2 billion spacecraft, the most sophisticated suite of instruments ever sent to the outer solar system. And there is a realistic possibility that after all 49 flybys, after years of data collection and analysis, the answer to whether Europa's ocean is habitable could still be probably, but we are not sure. Not because the spacecraft failed, not because the instruments did not work, but because the ocean is hidden beneath 30 kilometers of ice, and the signals we can access at the surface and in the atmosphere are intrinsically ambiguous. Science is comfortable with ambiguity. The public generally is not, and that gap between scientific comfort with uncertainty and public desire for definitive answers is where disappointment breeds. But there is another way to think about it. Even probably, but we are not sure, would be extraordinary. 40 years ago, the idea that a moon of Jupiter had a liquid ocean at all was speculative. 25 years ago, Kivelson's magnetometer data established that it probably did. 10 years ago, the composition of that ocean was almost entirely unconstrained. 5 years ago, we did not know it contained carbon. Today, we know the ocean exists, contains carbon, is in contact with rock, and has access to multiple energy sources. The trajectory of knowledge is unmistakable. Each decade brings not just new data points, but new categories of understanding. If Europa Clipper returns data showing that the ice shell contains subsurface lakes connected to the ocean, that the ocean's salinity falls within the range compatible with known biology, that trace atmospheric gases include molecules with plausible biological origins, that the seafloor shows thermal signatures consistent with at least some geological activity, then the case for habitability moves from compelling but incomplete to overwhelming. At that point, the question shifts from could life exist there to how do we go look for it? And that question drives the next mission. Which brings us to what Robert Pappalardo and others at JPL have spent nearly as long thinking about as the Clipper mission itself, the Europa lander. The concept has existed in various forms for more than a decade. The most detailed study, commissioned by NASA in 2016, produced a report describing a spacecraft that would touch down on Europa's surface in chaos terrain, deploy instruments to search directly for biosignatures in the ice, and attempt to access material that has recently been in contact with the ocean. The design called for a sterile sampling system that would scoop or drill into the top 10 centimeters of surface ice, process the samples, and analyze them with a suite of life detection instruments far more sensitive than anything on Europa Clipper. The lander concept addresses the fundamental limitation of the Clipper mission. Clipper flies past. It observes from a distance. It sniffs trace gases, but it never touches the surface. It never handles the ice. It never processes a sample. The lander would. It would sit on Europa's surface, in the exact terrain where ocean-derived materials are concentrated, and it would look for the molecular signatures of biology with instruments designed specifically for that purpose. But the lander faces challenges that go well beyond engineering. Europa's radiation environment would limit surface operations to roughly 20 days before the electronics accumulated a lethal dose. even inside a radiation vault. The spacecraft would need to land autonomously with no real-time ground control because of the 33 to 54-minute communication delay. It would need to be sterilized to an unprecedented level to prevent Earth microbes from contaminating the very surface it was trying to analyze for alien biology. Planetary protection requirements for a Europa lander are among the most stringent ever contemplated for any space mission. And the cost estimates, which run into the billions on top of Clipper's $5.2 billion, have kept the mission firmly in the concept category. For now, the lander waits. It waits for Clipper's data to make the case, to provide the compelling evidence that the ocean is habitable, to identify the specific surface locations where ocean material is most accessible. The lander is Clipper's intended successor, the second act in a story that NASA hopes will span decades. But whether Congress and future administrations fund that second act is a political question that no amount of science can guarantee. There is a deeper issue here, and it connects to the fundamental nature of the search for extraterrestrial life. We are looking for something we have never found. We have one example of life in the universe, and it all shares a single origin on a single planet. Every instrument we build, every mission we design, every chemical signature we search for is based on that one example. We look for water because our life needs it. We look for carbon because our life uses it. We look for energy gradients because our metabolism exploits them. We test for amino acids, lipids, nucleic acids, and metabolic byproducts because those are what our biology produces. If life on Europa exists but operates on fundamentally different chemistry, uses different molecules, exploits different energy sources, leaves different signatures, we might not recognize it even if we were standing on top of it. This is not a theoretical concern. It is an active area of research. Scientists have proposed alternative biochemistries based on silicon instead of carbon, ammonia instead of water, sulfuric acid as a solvent instead of water. None of these alternatives have been demonstrated in nature, and many have significant thermodynamic obstacles. But the point is that our search strategy is inherently biased toward life as we know it. We cannot search for what we cannot imagine. On the other hand, the chemistry of life on Earth is not arbitrary. Carbon is the backbone of terrestrial biochemistry because it forms 4 bonds and can create an extraordinary diversity of complex molecules. Water is the solvent because it has the right combination of polarity, hydrogen bonding capacity, thermal stability, and abundance. Energy gradients based on redox chemistry are universal in our biology because they are thermodynamically favorable and kinetically accessible. These are not random choices made by early Earth organisms. They reflect deep properties of physics and chemistry that would apply on any world. There are good theoretical reasons to expect that if life exists on Europa, it would be built on broadly similar chemical principles to life on Earth, even if the specific molecules and pathways differ in detail. This is why the habitability checklist looks the way it does. Liquid water, carbon chemistry, energy gradients, nutrients. It is not parochialism, it is physics. But physics does not guarantee biology, and this is the hardest part of the Europa story to communicate. Every discovery we have discussed, the ocean, the carbon, the salts, the energy, the geological pipeline, brings us closer to establishing that Europa's ocean meets the necessary conditions for life. Necessary conditions, not sufficient conditions. On Earth, the transition from prebiotic chemistry to biology happened once, roughly 4 billion years ago, and we do not understand how. We know the starting materials. We know the end result. We cannot describe the mechanism with confidence. The origin of life remains one of the deepest unsolved problems in science. If we do not fully understand how life started on Earth, where we have rocks to study, oceans to sample, and 4 billion years of geological and chemical context, how can we predict whether it started on Europa, where we have never touched the surface and have never sampled the ocean? We cannot. All we can say is that the conditions appear compatible. The rest is an open question. Let us return to the scientists, because their stories are not finished, and the personal threads running through this narrative connect to something larger than any individual discovery. Geronimo Villanueva, who led the JWST observation program that produced the carbon dioxide detection, holds the title of Associate Director for Strategic Science at NASA Goddard. He has received the Harold C. Urey Prize from the American Astronomical Society's Division for Planetary Sciences, one of the highest honors in the field for a scientist in the early to mid stages of their career. A minor planet has been named in his recognition, a small but permanent memorial in the asteroid belt to a researcher whose work has fundamentally changed what we know about Europa. Villanueva came to Europa science from a background in cometary and planetary atmospheres, and his team's expertise in spectral modeling is what allowed them to identify the CO2 as being mixed with water ice and methanol at a specific temperature, and to extract the carbon isotope ratio from a faint spectral feature at 4.38 micrometers that would have been noise in the hands of a less skilled group. Samantha Trumbo's trajectory through Europa science is unusually compressed. Her dissertation at Caltech, completed under Michael Brown, was built entirely around Europa, and it produced 2 landmark papers. The 2019 sodium chloride detection overturned a 2-decade assumption about the ocean's composition. The 2023 JWST carbon dioxide paper established the ocean as a source of biologically critical chemistry. She is now an assistant professor at UC San Diego, building her own research group and continuing to analyze JWST data for new insights into Europa's surface chemistry. Her combination of expertise in astronomy, biology, and oceanography is uncommon in planetary science, and it gives her a perspective that purely astronomical researchers sometimes lack. She thinks about Europa's chemistry not just as spectral features to be identified, but as a chemical system that either does or does not support the kind of molecular complexity biology requires. Kevin Hand's path to Europa science passed through some of the most extreme environments on Earth. His book Alien Oceans describes expeditions to glaciers, polar regions, deep sea environments, and hydrothermal vents, always with the same underlying question: how does life persist in the most challenging conditions our planet offers? And what does that tell us about where to look beyond Earth? The Europa in a Can experiment was not his most adventurous work. He once dove to the bottom of an ocean trench in a submersible with James Cameron, but it may have been his most consequential. By demonstrating that irradiated sodium chloride matches the color of Europa's chaos terrain, he provided the critical laboratory link between what Galileo saw and what the surface chemistry actually is. Without that experiment, Trumbo's 2019 Hubble detection would have been much harder to interpret. And then there is Kivelson. Margaret Kivelson, who began this story as a graduate student in the late 1940s and is still contributing to it in 2026. Her career spans the entire arc of planetary exploration, from the pre-spaceflight era through Pioneer, Voyager, Galileo, and now Europa Clipper. Her magnetometer data from the E2006 flyby remains the single most important measurement in Europa science. Everything else, the salt detection, the carbon detection, the ice shell measurement, the instrument suite on Clipper, all of it rests on the foundation she laid by demonstrating that the ocean exists. Kevelson holds the Royal Astronomical Society's Gold Medal in Geophysics, the American Astronomical Society's Gerard P. Kuiper Prize, and is a foreign member of the Royal Society. She was elected to the National Academy of Sciences. The recognition eventually came, decades after it should have, as is so often the case for women in physics. At 97, she represents a direct, living link between the generation that imagines subsurface oceans might exist on icy moons and the generation that is now building the spacecraft to explore them. Robert Papalardo's connection to Europa carries its own emotional weight. He was drawn to planetary science as an undergraduate at Cornell by Carl Sagan, the astronomer and communicator whose television series Cosmos inspired a generation to look at the solar system as a place of wonder rather than just a collection of astronomical data points. Papalardo earned his bachelor's degree from Cornell in 1986. Sagan died in December 1996, just as the Galileo spacecraft was beginning to return its first close-up images of Europa. Papalardo has noted that Sagan had the chance to see and be intrigued by some of the early Galileo Europa images before he passed away. There is something fitting about that. The man who taught the public to dream about other worlds got to see the first detailed pictures of what may be the most habitable world beyond our own, even if he did not live to learn what those pictures ultimately meant. Papalardo spent roughly 30 years working toward Europa Clipper, through periods when the mission was approved, then cancelled, then reconceived, then nearly killed by budget cuts, then revived, then threatened by the transistor crisis, and finally launched. That is, a career defined not just by scientific brilliance, but by endurance, the ability to keep working on a problem when the institutional support wavers, when the funding disappears, when the political winds shift, when the engineering nearly fails. Europa Clipper exists because of the science that justified it, but it also exists because people like Papalardo refused to let it die. This is a recurring theme in exploration. The missions that reshape our understanding of the universe are never just technical achievements. They are acts of sustained will by communities of people who believe a question is worth answering even when the answer takes decades to arrive. Now, let us imagine it is spring of 2031. Europa Clipper has been in Jupiter orbit for about a year. The first close flyby approaches. What happens? The spacecraft has spent months in a wide orbit around Jupiter. Adjusting its trajectory through gravity assists with Jupiter's moons, narrowing its path toward Europa. In the days before the flyby, ground controllers upload the detailed observation sequences that will control the spacecraft during the encounter. Every instrument's pointing, timing, and data collection mode has been planned years in advance, with adjustments made based on what earlier observations from orbit have revealed. As the spacecraft approaches Europa, closing from hundreds of thousands of kilometers to just 25, instruments begin their work. Reason sends radar pulses toward the surface, and the echoes return through the ice shell, carrying information about every layer, fracture, and density change they encountered on the way down and back up. MES maps the surface in infrared, identifying patches of concentrated salts, organics, and carbon dioxide with a resolution hundreds of times finer than JWST achieved. ETHEMIS scans for thermal anomalies, looking for spots where the ice is even slightly warmer than its surroundings, which could indicate subsurface activity or thin ice over a near-surface lake. EIS photographs the surface in stereo, building three-dimensional topographic models at resolutions sharp enough to see individual ice boulders. AMESPEX opens its inlet and breathes Europa's atmosphere, an atmosphere so thin it barely qualifies as one, capturing individual molecules and accelerating them through its multi-bounce flight tube to measure their masses with a precision of 1 part in 25,000. From those masses, the team can identify not just what species are present, but their isotopic ratios, which carry signatures of the processes that produce them. If the atmosphere contains hydrogen, it could indicate water rock reactions on the seafloor. If it contains methane, that could be geological or biological. If it contains trace organic molecules, the implications multiply. SUDA watches for tiny grains of material kicked off Europa's surface by micrometeorite impacts, catching them at relative velocities of kilometres per second, vaporizing them on impact with its detector surface, and analyzing the resulting ions. Each grain is a microscopic sample of Europa's surface chemistry, and SUDA can extract compositional information from individual grains weighing less than a femtogram. ECM records the magnetic field continuously, building a profile of how the field changes as the spacecraft passes through different geometric orientations relative to Europa's interior. Over 49 flybys, these profiles will map the ocean's magnetic signature in 3 dimensions, constraining its depth, extent, conductivity, and temporal variability. Europa UVS watches the limb of Europa against the blackness of space, looking for the faint, ultraviolet glow that would betray water vapor above the surface. If a plume is erupting somewhere on the visible hemisphere during this particular flyby, UVS will see it. The entire close encounter lasts a few hours. The spacecraft reaches closest approach, collects the most detailed data at minimum range, and then begins to pull away, climbing back into its wide Jupiter orbit. Over the next few weeks, as it moves farther from the intense radiation zone, it transmits the stored data back to Earth. At the distance between Jupiter and Earth, those radio signals travel for 33 to 54 minutes before reaching the Deep Space Network antennas in California, Spain, and Australia. The data rate is limited by distance and power. It takes time. All the data from one flyby might require days or weeks to transmit fully. Then the analysis begins. Different instrument teams work on their respective data. The radar team looks for layer boundaries and subsurface reflections. The spectrometer team maps chemical distributions. The magnetometer team models the induced field. Papers are drafted. Results are compared across instruments. Interpretations are tested against alternative hypotheses. This process takes months to years per flyby, and there are 49 flybys to analyze. The first few flybys will establish baselines. What does the ice shell look like in radar? What is the surface chemical distribution at high resolution? Does the magnetic field match the predicted induction pattern? Later flybys will target specific features identified in the early data, with observation sequences adjusted to maximize coverage of the most scientifically interesting sites. If early flybys reveal a thermal anomaly in chaos terrain, later flybys might be reoriented to fly directly over it, with E-Themis at maximum resolution. The timeline from first flyby to comprehensive results will span years. This is not a single dramatic moment of discovery. It is a sustained campaign of observation and analysis, building understanding incrementally. The public will see press releases announcing individual findings as they are confirmed. A radar image showing a possible subsurface lake, a chemical map revealing an unexpected concentration of some compound, a magnetic measurement that refines the ocean depth estimate. Each result will be a piece of the puzzle. The full picture will not emerge until well into the 2030s, after the mission is complete and the accumulated data from all 49 flybys has been analyzed in aggregate. And what picture might emerge? The range of possibilities is wide. At one extreme, Europa Clipper could find unambiguous evidence that the ocean is habitable, with subsurface lakes connected to a warm, salty ocean in contact with an active seafloor, with trace atmospheric gases indicating ongoing chemical reactions consistent with biological processes, with surface chemistry rich in complex organics that bear the hallmarks of biological production. This would be the best case from an astrobiology perspective, and it would almost certainly trigger immediate efforts to fund a lander mission. At the other extreme, Clipper could find that the ice shell is thick, featureless, and static, with no evidence of subsurface lakes or recent geological activity, that the ocean is either extremely dilute or extremely briny, outside the range where known biology operates, that the seafloor is cold and inert, with no thermal signatures of hydrothermal activity, that the atmosphere contains no trace gases beyond what radiation physics on the surface would produce. This would not mean life is impossible. Absence of evidence is not evidence of absence, especially from a flyby mission, but it would mean the case for sending a much more expensive lander weakens considerably. The most likely outcome lies somewhere in between. Some evidence suggesting habitability, some evidence introducing complications, a mixed signal that advances understanding enormously but does not deliver a clean verdict. This is the typical outcome of exploration. It is what Galileo delivered. It is what JWST delivered. It is what science usually delivers. The clean, definitive, headline-friendly answer is the exception, not the rule. There is a final thought experiment that captures the full weight of what this story is about. Imagine you could somehow transport yourself to the floor of Europa's ocean. You stand in complete darkness on a rocky seafloor, in water near the freezing point, under an ice ceiling 30 kilometers above your head, and an ocean 100 or more kilometers deep, pressing down around you. The pressure is over 1,000 atmospheres. There is no sound except the distant groaning of ice shifting under tidal stress. What is around you? We do not know. Maybe nothing. Maybe the bare rock and cold water and silence of a world that has all the ingredients and none of the outcome. A world where the chemistry was right, but the spark never caught. Where 4.5 billion years of water and carbon and energy produced nothing but water and carbon and energy. Or maybe the rock beneath your feet is warm in places, and from those warm spots, chemical-rich water seeps into the ocean, carrying minerals and dissolved gases. Maybe near those seeps, in the slight warmth and the chemical gradients, something lives. Not organisms you would recognize, not fish or shrimp or anything with a body plan evolved in sunlight. Something simpler, something ancient, something that has been metabolizing slowly in the dark for longer than complex life has existed on Earth. Microbial communities clinging to mineral surfaces, exploiting chemical gradients so subtle that they would be undetectable from orbit, living so slowly that a single generation spans a human lifetime. This is not science fiction. Every element of this scenario has an analog on Earth. Microbial communities have been found in deep continental rock, kilometers below the surface, living in isolation from the sun-driven biosphere for millions of years. Organisms at hydrothermal vents thrive in darkness, at high pressures, in water saturated with chemicals that would be toxic to surface life. Life at the bottom of Antarctic ice-covered lakes persists in conditions that are at least loosely analogous to what Europa's ocean might offer. None of these terrestrial analogues prove anything about Europa, but they demonstrate that the combination of conditions Europa appears to have, water, rock, chemical energy, darkness, pressure, cold, time, is a combination that life on Earth has figured out how to exploit repeatedly in many different environments. The question is whether that capability is specific to Earth's life, a product of our particular history and our particular biochemistry, or whether it is a general property of chemistry under the right conditions. Whether the origin of life is so improbable that it happened once in the observable universe and we are it, or so inevitable that it happens wherever the conditions allow, including in a dark ocean under an ice shell on a moon of Jupiter. Europa Clipper will not answer that question. No single mission can, but it will narrow the space of possible answers in ways that nothing before it could. It will tell us whether the necessary conditions are met with enough specificity that the next question, is anything alive, becomes answerable in principle. And that is what makes this mission worth $5.2 billion and 13 years of development and a terrifying transistor crisis and 5 years of interplanetary travel. On November 23, 2022, the James Webb Space Telescope collected a few minutes of infrared light from a small moon orbiting Jupiter. From that light, 2 teams of scientists extracted a signal, carbon dioxide on the surface, from the ocean below. The signal was clear. The interpretation was robust. The implications were enormous. But the signal was also, in the end, a few photons of reflected sunlight that had bounced off a patch of ice on a world 800 million kilometers away. That is all we had. A whisper from an ocean we have never seen, carried by light across a gulf of space so wide that the signal was more than half an hour old by the time it reached us. And from that whisper, from those photons, from the painstaking analysis of spectral features at 4.25 micrometers, an entire generation of scientists has built the case that somewhere in the outer solar system, beneath kilometers of ice, in perfect darkness, in water we have never touched, the conditions for life might exist. Might. That word carries the full weight of everything we have discussed. It is the word that separates what we know from what we hope. It is the word that Europa Clipper was built to interrogate. And it is the word that will define the next decade of planetary science. Kurt Niebuhr, Europa Clipper's program scientist, said something at the October 2024 launch that stopped people in their tracks. If our solar system turns out to be home to 2 habitable worlds, think of what that means when you extend that result to the billions and billions of other solar systems in this galaxy. 2 habitable worlds, Earth and a frozen moon of Jupiter, where an ocean we have never seen might harbor life we have never imagined. Kevin Hand, whose career has taken him from the deepest oceans on Earth to the ice of Antarctica to the vacuum chambers of JPL, all in pursuit of understanding where life can exist, wrote something in his book that captures the scope of what this is all about. He imagined a universe where Europa's ocean, or oceans like it, on worlds we have not yet discovered, harbor life. And if they do, then the tree of life we know on Earth, from microbes to whales, from bacteria to redwoods, from archaea in volcanic springs to humans reading these words, all of it might be just one small branch. He wrote that perhaps we live in a universe of incredible biological diversity across planets, moons, stars, and galaxies. Perhaps our tree of life is but a tiny twig on a tiny branch, joined to a vast and grand tree. Perhaps in 4.5 years, we will know more. In 10 years, we might know enough to send a lander. In 20 years, a drill. Maybe, someday, a submarine that descends through 30 kilometers of ice into an ocean twice the size of everything on Earth, carrying a light into the darkness for the first time. Or maybe not. Maybe the ocean is empty. Maybe the chemistry never caught. Maybe Europa is a monument to the narrowness of the path from ingredients to life. A world that had everything and produced nothing. And the silence of its ocean is the answer. Either way, we will have looked. And either way, the answer changes everything. But let us not end there, because there is a piece of this story we have not fully explored, and it connects the technical science to something more human. It is the story of how Europa Clipper almost did not happen at all, not because of transistors, but because of politics, money, and the particular cruelty of how American space exploration is funded. The idea for a dedicated Europa mission stretches back to the mid-1990s, when Galileo's first images of chaos terrain and its magnetometers' first hints of an ocean made it clear that this moon deserved more than a handful of flybys from a spacecraft with a broken antenna. In 2000, a mission concept called the Jupiter Icy Moons Orbiter, JIMO, was proposed as part of NASA's Project Prometheus, an ambitious plan to develop nuclear electric propulsion for deep space missions. JIMO would have orbited each of the 3 icy Galilean moons in turn, Callisto, Ganymede, and finally Europa, conducting months of observations at each. It would have carried an ice-penetrating radar, a laser altimeter, and a sophisticated instrument suite far beyond anything that had been sent to Jupiter before. JIMO was cancelled in 2005. The nuclear propulsion technology it depended on was too immature. The costs were escalating toward an estimated $16 to $18 billion, and NASA's priorities were shifting toward the Constellation program to return humans to the moon. For the Europa community, it was the first of many disappointments. In 2008, NASA and the European Space Agency jointly proposed the Europa-Jupiter system mission, which would have sent 2 spacecraft to the Jupiter system, 1 American and 1 European, to study Europa and Ganymede, respectively. ESA's half of the mission eventually evolved into JUICE, the Jupiter Icy Moons Explorer, which launched in April 2023 and is currently en route to Ganymede. But the American half was repeatedly descoped and reformulated as budget pressures mounted. It was called the Jupiter-Europa Orbiter for a while. Then it became the Europa Multiple Flyby Mission. Then, finally, Europa Clipper. The name itself tells you something about the compromises. The original concept was an orbiter, a spacecraft that would settle into orbit around Europa and observe it continuously. An orbiter would spend months or years in the radiation environment, which would destroy its electronics quickly. The Clipper concept, proposed by Robert Pappalardo and his JPL colleagues, was an elegant solution. Instead of orbiting Europa, orbit Jupiter on a wide elliptical path and clip past Europa repeatedly, spending only hours in the worst radiation instead of months. You lose the continuous observation, but gain survivability. The name comes from the clipper ships that sailed fast routes in the 19th century, and it stuck because it captured the mission's defining characteristic: speed through danger, then retreat to safety. Again and again, 49 times. Even as Europa Clipper, the mission faced repeated threats. Congress had to authorize it over NASA's own objections in some years. The Space Launch System was originally mandated as the launch vehicle, which would have been more expensive and complicated, but politically attractive because it kept the SLS production line busy. When that requirement was eventually relaxed and SpaceX's Falcon Heavy selected instead, the savings were significant, but the political dynamics shifted. Appropriations committees questioned the cost. Competing missions lobbied for the same budget. Every fiscal year brought another survival test. The mission survived because of a combination of scientific merit, political skill, and public fascination. Europa consistently polls as one of the solar system destinations the public finds most compelling. The one word that explains why is ocean. An ocean beneath the ice of a moon of Jupiter. The concept is viscerally compelling in a way that spectroscopy results and magnetometer data are not. People understand oceans. They understand the idea of hidden water. And they understand at an intuitive level the question of whether something might be swimming in it. That public fascination translated into political support. Members of Congress, particularly John Culberson, who represented Houston's 7th Congressional District and chaired the House Commerce, Justice, and Science Appropriations Subcommittee, championed Europa Clipper with an intensity that bordered on personal mission. Culberson was a space enthusiast who had been captivated by Europa since the Galileo results, and he used his position to direct funding toward the mission even when NASA headquarters was lukewarm. Without his advocacy, Europa Clipper might have died during one of its many near-death experiences in the appropriations process. Culberson lost his seat in the 2018 midterm elections, but by then, the mission had enough momentum and institutional support to survive. The formal mission confirmation, the point at which NASA commits to a specific design, budget, and launch date, came in 2024. From first concept to launch, Europa Clipper took roughly 25 years. Pappalardo was involved for nearly all of it. There is a parallel here that is worth drawing. Europa's ocean has existed for roughly 4.5 billion years, patiently waiting beneath the ice, and the mission designed to study it took a quarter century to get off the ground. In the grand scheme of things, 25 years is nothing. But to the humans who spent those years fighting for it, writing proposals, testifying before Congress, redesigning instruments, surviving budget cuts, and then facing a transistor crisis 5 months before launch. It was a career, several careers. The patience required to do planetary science, to ask a question and then wait decades for the spacecraft that will provide the data to answer it, is a quality that does not get enough attention. It takes a particular kind of person to commit their working life to a question whose answer will arrive, if it arrives at all, near the end of that life. Kivelson published the definitive ocean evidence in 2000. Europa Clipper launched in 2024. It arrives at Jupiter in 2030. The first science results will come in 2031. From ocean discovery to first detailed investigation, 31 years. Kivelson was 72 when she published the paper. She will be 102 when the first flyby data reaches Earth. The timescales of planetary exploration exceed individual human lifetimes, and the scientists who start the work are rarely the ones who finish it. But sometimes, if they are tenacious enough and fortunate enough, they live to see the beginning of the answer. This brings us to a question that runs beneath all the science and engineering and politics. Why does it matter? Not in the grant proposal sense, but you justify funding by listing potential benefits. In the human sense, why do thousands of people spend decades of their lives studying a moon they will never visit, an ocean they will never swim in, organisms they may never find? Part of the answer is curiosity, which is real and sufficient on its own. Humans have always wanted to know what lies beyond the horizon, beneath the surface, inside the box. Europa is the biggest box we have found, an ocean larger than all of Earth's, sealed away from us by ice and distance and the laws of physics. The desire to know what is in it is the same desire that sent ships across unknown oceans and drills into unknown rock. It is the desire that built telescopes and accelerators and the James Webb Space Telescope itself. But there is another part, and it is the part that Pappalardo and Hand and Niebuhr and the others articulate most clearly when they speak publicly about the mission. It is the question of whether we are alone. Not alone in the philosophical or emotional sense, though that matters too. Alone in the biological sense. Whether the origin of life is a freak accident, a one-time event of such astronomical improbability that it happened once in a universe of 2 trillion galaxies and 100 billion stars per galaxy and trillions of planets, or whether it is a natural chemical process that occurs reliably whenever conditions permit. If life exists on Europa, independently from Earth, evolved from scratch in a separate ocean on a separate world, it would answer that question. It would tell us that the origin of life is not freakishly unlikely, that given the right conditions, chemistry becomes biology, that the universe makes life the way it makes stars, naturally, inevitably, wherever the physics allows. The implications would be staggering, and they would extend far beyond astrobiology. If 2 worlds in our single solar system both produced life independently, the probability calculations for the rest of the galaxy and the rest of the universe shift from uncertain to overwhelming. The number of living worlds in the Milky Way alone would go from somewhere between 0 and billions to somewhere between billions and hundreds of billions. The universe would be, as Hand put it, teeming. But the converse is also profound. If Europa's ocean has had water, carbon, energy, and time for 4.5 billion years and produced nothing, if all the ingredients are there and the recipe still did not work, it would tell us something dark, about the origin of life. It would suggest that whatever happened on Earth 4 billion years ago was even more unlikely than we thought. That having the conditions is not enough. That there is some step, some barrier, some bottleneck in the transition from chemistry to biology that the right conditions alone cannot guarantee. This is sometimes called the Great Filter in discussions of the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilizations and the lack of evidence for them. If the filter is behind us, if the hard step was the origin of life and we already passed it, then the silence of the universe might just mean life is rare, but we are among the lucky ones. If the filter is ahead of us, the implications are darker. But either way, Europa's ocean offers a data point. One data point from one world, but it will be the first data point beyond Earth about whether life arises when conditions permit. One data point. That is what 50 years of exploration and $5.2 billion and 9 instruments and 49 flybys and the sustained effort of hundreds of scientists might produce. Not a definitive answer, a data point. And yet that single data point could be the most important measurement in the history of biology. Because right now, the sample size for independently originated life in the universe is 1 Earth. Everything we know about life's probability in the cosmos is extrapolated from a sample of 1. Adding a second data point, whether positive or negative, would be transformative. Think about what it means to have a sample size of 1 for the most fundamental question in biology. It is as if you flipped a coin once, got heads, and then tried to determine the probability of heads based on that single flip. You know it is somewhere between 0 and 100%, but that range is not useful. A second flip, heads or tails, immediately constrains the estimate. It does not give you a final answer, but it tells you something the first flip alone never could. Europa is the second flip, and that, in the end, is why the carbon matters, why the salt matters, why the ice thickness matters, why the plume non-detection matters, why the transistors matter, why the mission matters. Not because any one of these results tells us whether life exists in Europa's ocean, but because together they define the conditions of the experiment. They tell us what the coin is, how it is weighted, what the odds might be. They set the stage for the moment when Europa Clipper's instruments tell us whether the conditions for life are met with enough specificity that the question, is anything alive, becomes a question science can actually address. That moment is still years away. The spacecraft is still in transit. The ice has not yet been sounded. The atmosphere has not yet been sniffed. The magnetic field has not yet been mapped from close range through 49 geometries. But the trajectory is set. The instruments are built and tested. The transistors will anneal. The gravity assists will provide the energy to reach Jupiter. And in the spring of 2031, the first data will begin its 33 to 54-minute journey back to Earth. A few minutes of photons from a telescope in 2022 changed what we know about Europa's ocean. A few years of data from a spacecraft in the 2030s will change what we know about life in the universe. The ocean waits. It has been waiting for 4.5 billion years. It can wait a little longer. There is one more thing worth understanding about Europa before we leave this story, and it concerns the mechanism that makes everything else possible. Tidal heating. Because without it, there is no ocean. Without it, Europa is just another frozen rock in the outer solar system, its water permanently locked in ice, its chemistry inert, its potential unrealized. Tidal heating is the engine that keeps the ocean liquid, and the physics behind it is both elegant and slightly counterintuitive. Europa orbits Jupiter at a distance of roughly 671,000 kilometers, completing one orbit every 3.5 Earth days. If it were alone in the Jupiter system, its orbit would have circularized long ago due to tidal dissipation, and without orbital eccentricity, there would be no tidal flexing, no internal heating, and no liquid ocean. But Europa is not alone. It shares the Jovian system with Io and Ganymede, and the three moons are locked in a gravitational relationship called the Laplace resonance. For every 4 orbits Europa completes around Jupiter, Io completes 8, and Ganymede completes 2. This 1:2:4 ratio is exact and self-maintaining. It has persisted for hundreds of millions and possibly billions of years. The resonance forces Europa's orbit to remain slightly elliptical with an eccentricity of about 0.009. That does not sound like much. The orbit is nearly circular, but nearly is doing enormous work here. Because of that tiny eccentricity, Europa's distance from Jupiter varies over the course of each orbit. When it is closer to Jupiter, the tidal bulge raised on Europa by Jupiter's gravity is slightly larger. When it is farther away, the bulge is slightly smaller. This means the ice and rock of Europa are being continuously flexed, stretched, and compressed in a regular rhythm synchronized to the orbital period. And when you flex solid material repeatedly, it generates heat, the same way bending a paperclip back and forth makes it warm. The total tidal heat generated in Europa is estimated at roughly 1 terawatt, which is about 1/5 the total geothermal heat output of Earth. Spread over Europa's surface area, this comes to roughly 30 milliwatts per square meter. That is a small number per unit area. For comparison, Earth's average geothermal heat flux is about 90 milliwatts per square meter. But it is enough. Over the billions of years since the Laplace resonance locked into place, this steady drip of tidal energy has kept Europa's deep interior warm enough to maintain liquid water beneath the ice shell. Where exactly the tidal heat is deposited within Europa matters more than the total amount. If most of the dissipation occurs in the ice shell, the shell will be warmer, convection within the ice will be more vigorous, and material transport between the surface and the ocean will be easier. If most of the dissipation occurs in the rocky mantle, the seafloor will be warmer, hydrothermal activity will be more likely, and the chemical energy available at the ocean floor increases. Both scenarios support the ocean, but they produce different kinds of habitability. Current models suggest the answer is probably some combination of both. The ice shell almost certainly convects, with warm ice rising and cold ice sinking in slow, churning circulation patterns that take thousands to millions of years to complete one cycle. This convection is likely part of what drives chaos terrain formation, as warm ice diapirs reach the surface and disrupt the cold, brittle crust above. Meanwhile, at least some tidal dissipation occurs in the rocky interior, keeping the mantle warm enough for at least low-level geological activity. The Laplace resonance also has implications for the long-term stability of the ocean. Unlike some heating mechanisms that are transient or episodic, the orbital resonance provides a steady, predictable, essentially permanent heat source. As long as Io, Europa, and Ganymede remain in resonance, Europa will be tidally heated, and orbital dynamics calculations suggest the resonance is stable on timescales of billions of years. This means Europa's ocean is not a temporary phenomenon. It is a permanent feature of the Moon, maintained by the gravitational architecture of the Jupiter system. Compare this to Enceladus, whose tidal heating source is less certain. Enceladus orbits Saturn in a 2-to-1 resonance with Dione, and the total tidal heat budget is estimated at roughly 15 to 18 gigawatts, perhaps higher. But there is an ongoing debate about whether the current level of activity on Enceladus is sustainable over geological time, or whether it represents a temporary peak that will eventually subside. Some models suggest the plume activity observed by Cassini might be a geologically recent phenomenon, perhaps only 100 million years old or less. If Enceladus's ocean is younger than Europa's, it has had less time for prebiotic chemistry to do its work. This brings us to one of the most philosophically loaded questions in astrobiology. How long does it take for life to originate? On Earth, the geological record suggests that life appeared relatively quickly once conditions became suitable, perhaps within a few 100 million years of the late heavy bombardment, and possibly even earlier. Some interpretations of carbon isotope fractionation in rocks from Greenland push the date back to 4.1 billion years ago, barely 500 million years after Earth formed. If that timeline is correct, life on Earth originated fast by geological standards, but fast is a relative term. 500 million years is still 500 million years. If the origin of life requires rare events, unlikely molecular configurations, or specific environmental conditions that occur only in narrow windows, then even 500 million years might represent a lucky break rather than an inevitable outcome. On a smaller moon with a younger ocean, the odds might be lower, simply because there has been less time for the right combination of events to occur. Europa's ocean addresses this concern directly. If the ocean has been liquid for 4.5 billion years, as the Laplace resonance stability calculations suggest, then any prebiotic chemistry has had the same time frame as life on Earth, the same 4.5 billion years, the same opportunity. If the origin of life is a function of time and conditions, Europa has had enough of both. And then there are the environments on our own planet that serve as imperfect but instructive analogues for what Europa's ocean might be like. The most commonly cited is Lake Vostok in Antarctica, buried beneath roughly 4 kilometers of ice. Lake Vostok has been isolated from the surface for approximately 15 million years, maintained in liquid form by geothermal heat and the insulating properties of the overlying ice sheet. When Russian scientists drilled into the lake in 2012, they found water. Whether they found life in that water remains debated. Contamination from drilling fluid made it difficult to distinguish between organisms native to the lake and microbes introduced from the surface during the drilling process. But the lake itself, a body of liquid water sealed beneath ice for millions of years, demonstrates that the basic physical setup of Europa's ocean exists on Earth, and that water can remain liquid under thick ice for very long times. More relevant, perhaps, are the microbial communities found in Earth's deep continental crust. In South African gold mines, at depths of 2 to 3 kilometers below the surface, researchers have found bacteria living in fracture water that has been isolated from the surface for tens to hundreds of millions of years. These organisms metabolize using chemical reactions between water and rock. Specifically, the radiolysis of water by natural radioactivity in the surrounding rock, producing hydrogen, which bacteria then combine with sulfate dissolved in the water. The energy yield is tiny. The organisms grow so slowly that a single cell division might take thousands of years, but they are alive. They are metabolizing. They are reproducing. And they are doing so in conditions that, while not identical to Europa's ocean, share some of its key characteristics: darkness, isolation, rock-water interaction as the primary energy source. Geological timescales of existence. The Lost City hydrothermal field on the mid-Atlantic ridge provides another analog, perhaps a better one, for what Europa's seafloor chemistry might look like if hydrothermal activity is present. Unlike the famous black smoke events, which are powered by volcanic heat and produce superheated, acidic, metal-rich fluid, Lost City is driven by a chemical process called serpentinization, when seawater infiltrates ultramafic rock, specifically peridotite. The iron and magnesium in the rock react with water to produce serpentine minerals, magnetite, and large quantities of hydrogen gas. The resulting hydrothermal fluid is warm, roughly 40 to 90 degrees Celsius, not superheated, and highly alkaline, with pH values around 9 to 11. The hydrogen produced by serpentinization provides chemical energy that microbial communities exploit, and some researchers have argued that alkaline hydrothermal systems like Lost City may have been the cradle where life on Earth originated. If Europa's seafloor contains ultramafic rock, and there are reasons to think it might, based on models of Europa's formation and differentiation, then serpentinization reactions could be occurring. The hydrogen produced would provide a reduced chemical species that, combined with oxidants delivered from the surface, creates the kind of redox gradient that organisms could exploit. This is the scenario many astrobiologists consider most likely for Europa, not the dramatic black smoker model with superheated volcanic fluid and towering mineral chimneys, but the quieter, cooler, alkaline chemistry of serpentinization, less photogenic, possibly more important for life. The 2026 Byrne study does not rule this out. What it cautions against is the assumption that Europa's seafloor is as geologically vigorous as the most active regions of Earth's ocean floor. The total heat output is lower. The tidal dissipation in the mantle may be modest. The seafloor might be warm in places, with modest hydrothermal systems, rather than hot everywhere with dramatic volcanic activity. This is actually consistent with the serpentinization-driven system, which requires relatively low temperatures and modest water-rock interaction rates. The quieter seafloor that Byrne's models predict might be exactly the right temperature for the kind of alkaline hydrothermal chemistry that Lost City exhibits on Earth. So even the study that introduced the most significant new uncertainty into the habitability picture does not necessarily make the case worse. It changes the expected character of the ocean's energy sources. It shifts the balance from high-energy volcanism toward low-energy water rock chemistry. And low-energy water rock chemistry, as the deep biosphere and Lost City demonstrate, is perfectly capable of supporting life. This is what makes Europa's story so compelling and so frustrating at the same time. Every new piece of information simultaneously clarifies and complicates. Every question answered spawns two more. The picture gets sharper in some areas and blurrier in others, and the overall trajectory is towards greater understanding without ever quite reaching resolution. That trajectory will continue for decades. Europa Clipper's data will take years to fully analyze, Any follow-up mission, a lander, a drill, a submarine, would take another decade or more to develop and fly. The definitive answer to whether Europa's ocean supports life, if a definitive answer is achievable at all, lies somewhere in the 2040s or 2050s at the earliest. Most of the scientists currently working on Europa will have retired or died before that answer arrives. They know this. They work on it anyway. There is a quality to planetary science that distinguishes it from almost every other human endeavor. The timescales are not human timescales. The questions span generations. The investments made today pay off in the careers of scientists who are currently in grade school or not yet born. The people who conceived of a Europa mission in the late 1990s knew they might not live to see it launch. The people who built Europa Clipper know they might not live to see its most important results fully analyzed. And the people who will eventually analyze those results will owe their opportunity to decisions made before they were old enough to choose a career. This is how we explore, not in single heroic leaps, but in relay. Each generation carries the question a little further, hands it to the next, and trusts that the effort was worthwhile, even if the answer comes later than hoped. Kivelson proved the ocean exists. Trumbo proved it contains carbon. Hand proved the surface salts come from below. Pappalardo shepherded the mission through 30 years of political turbulence. Someone not yet named will analyze the first flyby data. Someone else, not yet named, will design the lander that follows. And someone else, decades from now, will look at the data from that lander and know, finally, whether the dark ocean beneath the ice is alive or empty. The question has been open for 50 years. Europa Clipper is on its way. The ocean waits.